a little bit. And then what I will do is, because in the middle of somewhere presentation, I also intend to make some hands-on presentations also, so that you get some idea of how to use the tools. So yes, electronics, we are from all electronics domain, and in the last couple of decades, it's been really entertaining. We have seen so much growth in various domains like entertainment, medical, transportation, competitions, communication, defense. But there is one problem I see, that many of the students, when they are told that how electronics have changed lives, they can't answer properly. Okay. So some of the answers they know, because these examples are very simple. Because, for example, if you take gaming industries, so yes, because of the germination of the GPU, CPU power, computing, we have seen more complex softwares in the gaming, and you can render more complex games. And hence, you have seen the evolvement of the uh, gaming industry. Telecommunication is very easily understood by the students, because they have seen iOS or the iPhone and the Android generally, and they have seen how and heavy and bulky mobile phones are replaced with the lightweight mobile phones, which can run the battery for hours and hours, and can do really amazing tasks. I mean, today's mobile phone is as good as my CPU or a computing desktop around a decade back. So it's amazing computing power we have in our hand. The other thing is like automobiles. We have seen a huge evolution, and probably we are almost on the verge of a next generation of evolution in terms of electric vehicles. Now, here comes that how electronics have changed the way the tech products are made. Because in this prima facie, I mean, a very commonly used technology in BLDCs is the BLDC in the electric vehicles. Now there comes a BLDC is just a brushless DC motor. This idea was known from the last, what, the since of birth of DC motors. So how come electric vehicles are electric all in total? Because of the electric motor they use, which is BLDC. So the question comes up that how they do the things. Okay, so many students, they are hardly informed on this, that in a DC motor, we teach them that there are three coils and there are three, I take all the coils, okay, and you take the wiring. So there is a brush commutation who gives power or distributes power at 120-degree apart to the DC motors. And we see the circulation of the rotor. Now comes the birth of microcontrollers who can execute control loops in much more higher frequencies. And hence, instead of unbrushed, you can remove that, and you can simply put a MOSFET to drive these DC motors. You can just drive this DC motor with the help of the MOSFET. And since they are applied with the PWM signal, which is more than 30 kilohertz. To give that at 30 kilohertz, you need to have a microcontroller who can do the complex computations at more than hundreds of megahertz. Okay, so this was only possible around 15 years back. And since then only, the dominance of BLDC motors started. Okay, uh, but any student can ask, is sir, okay, 30 kilohertz requires 100 megahertz CPU. Why can't I have 5 kilohertz, okay, PWM on a 10 megahertz CPU? Yeah, this is possible, quite possible. But the problem is a 5 kilohertz uh, BLDC motor who's running on a PWM will generate the noise or the sound which our ears can easily capture. And we will have a very irritating sound while driving the electric vehicles. So that no one car designer will have. So everything is about 20 kilohertz range beyond the human audio range. Okay, moving forward and look at the electronics that has brought in the ADAS. We are already at level 3 and 4. And we have already seen autonomous driving. This is all possible with the birth of the electronic. Medical devices, amazing. Now we have all the gadgets on our wrist, like wristbands and smartwatches, who can measure your oxygen, ECGs even. So this is beautiful. Even in the defense, I mean, I believe everyone must have heard of this radar, S400. Okay. So earlier days, we know that these were the scan arrays, antennas were there, which used to rotate 360 to identify the incoming aircrafts. But if you have heard the news that during the Operation Sindhu, we have used the Russian S400 radar communication equipment, which is not having any mechanical movement, moving part. Instead of that, they have electronic scan array antennas. So that means this is only possible because of the high-speed FPGAs, which can generate signals and capture back the signals and process them at a very high frequency possible. Okay, so that was all possible because of the electronics performance that we have due to semiconductor. Okay. Computing, there is no need to explain in detail that how things are going it. Okay. So this is the forefront of the technology for the semiconductor. Any semiconductor device or technology which has been released, they are targeting this particular market segment. Okay. Because there's the workstations and servers and the laptops and gadgets, which are the primary customers for the semiconductor companies. And one of the beautiful example, we have progress from bonfire or simple fire-based lighting to LED lamps. This progression is only possible due to semiconductors. Okay, so as we are all aware of that, the key driver between all this electronic explanation, explosive growth is because of a semiconductor chip, for which we are all familiar about. Okay, so all Moore's law that we live through, that the amount of transistors that can be pumped, will be pumped in a semiconductor chip area would be doubled after every 1.5 years. Okay. So let's have a look around that how the roadmap has been progressed in the last maybe couple of decades. Okay. So what kind of changes have been in the market and what are the things lying up in the future? Okay. So basically, if you see around, there are three transistors family which are available in the market today. Uh, I can't say of the nanosheet because not today, but immediately in this coming future, they would be available in the market. So MOSFET, we are all familiar about. Okay. So probably I won't be talking about MOSFET because this is a thing which is available in the textbook from decades. And probably FinFET is about to enter the textbook. I have seen syllabus of some universities where this is a part of the curriculum. Okay. And nanosheet, which is upcoming technology. Okay. And that would be the next gen transistor that we will see through. So the later part of the transistors we will talk about. Okay. Mm. So at this point of time, maybe I just start generally with the students I always engage, and it's good to engage with the faculties also. And the question is that if you see the progress of this VLSI roadmaps or the semiconductor industry, a very prevalently used transistor technology is MOSFET. Okay. So a very basic question that why CMOS was so popularly used. Why not any other transistor technology was prevalently or maybe was able to challenge the progress of MOSFET? Anyone? Yes, the prima facie, if you ask kids about this question, they all answer in three, four points. Some people say that it's a high performing device. Some kids say it's a low power device. And some say that is easy to fabricate, or some say that scaling is possible in MOSFET. So I just want to hear that what is your opinion on these points, or maybe something else you can add with. I just open the chat box. I see some messages over there. Ouch. Mm-hmm. Okay. Low power, high packaging density, scaling can be done. Yes, Deshmukhji, yes, that's a good one. So if you ask me that what is my order, so I always rate as an engineer that easy and easiness, or you can say the comfort in scaling of the design is a very important feature for a MOSFET technology. Because if we take a MOSFET transistor technology, let's say you are working on 90 nanometer, and by the Moore's law, or probably the company is investing in the next upcoming fabrication, which is 65. So obviously, I can't re-engineer the entire layout and take that layout into another scaled design and design the entire chip from the ground up. So many of the companies, what they do, the transistors allows, especially the MOSFET, they take the previous design, scale up to the newest technology, adjust some of the features or the issues generated by the layout scaling, and go with the fabrication for the next gen. So that becomes very easy. So that is why they are able to release every year a new chipset possible. So this was only possible with MOSFET because the scaling is easy. Yet, if you ask me the second and most important one, second most important, so I would say they are low power and at the same time they have very high integration. You can have very compact layout designing as compared to the other transfer technologies. I'm sorry. Okay. Yes, scaling with symmetric structures, noise margins can be on the last ones. And what is the minimum thickness of the Si2? Santoshji, that depends on the what fabrication tech. So from 2 nanometers to multiples of nanometer, silicon dioxide thickness is changed by technology. Okay. And yes, their design versatility means you can design digital circuits, you can analog design or mixed designs. All are possible with CMOS technology. So given all, CMOS is an overall guide to have it. Okay. The another aspect which kids wants to understand, or generally the kids in my sessions they ask is, so why is it so necessary to scale? Is it really necessary to scale? And is it very necessary to keep the Moore's law alive or to invest so heavily? Because whenever we talk about fabrication, we talk about that's a multi-billion-dollar investment or putting the fabrication plant just to scale from one technology node to another one. So some kids do really want to know that why we want to do that. The point is, yes, the scaling offers 2x in the density. They offer 30% improvement in speed, more or less, and 30% reduction in power. Okay. And obviously, the leakage currents are reduced because you are making the transistor smaller and smaller. So obviously, less area, smaller leakage. But before answering, I should have put in an animation for that. That's okay. But before answering that, if you look, we all are familiar that the Moore's law has governed the scaling graph. So that is one. Okay. So if you pick up any technology node, let's say I pick up this is 0.18 micrometer, and I just open my calculator. So that is what 180 nanometer. So we know that Moore's law talked about scaling the size of the transistor by 30%. Okay. So that means if I draw and square, which is not perfect one, but still will do. So this is, let's say 1x by 1x, and I scale this by what, 30%. So this new size becomes 0.7 part of my drawing. Okay. So previously the area was 1 square some unit. 30% reduced size means it is like 0.49 or 50% of the previous area. So now if I pick up a technology node, let's say 180 nanometer, and multiply this by 0.7, that is a reduction of 30%. Okay. So I get the next technology node, which is around 130 nanometer or 0.13 micrometer. I just multiply this by 0.7. I get the next technology node, which is 90 nanometer. And I take 90, multiply by 0.7, I get next technology node 65. I multiply by 0.7, 45, multiply by 0.7, I get 32, and so on. Okay. So a simple thing that I reduce the size of the transistor by 30% and I get twice the area advantage, and that's it. Okay. I get 30% reduction in power because obviously you have reduced the size by 30%. So more or less, that is what the equations talk about. But the thing is, if you take a silicon wafer, and earlier you were able to manufacture what, let's say 100 numbers of Core i7 CPUs out of it, and you sell every CPU at $100, So in the next technology node, instead of 100, you will be able to fabricate a tentative number of 200 CPU dies. So, and let's say even though you sell at $90 a unit by reducing the cost by telling your customer that since the scaling has happened, things are smaller, we are reducing the cost by $10, still you make $180 out of the previous budget. Okay, so the margins also almost doubles for the companies. That's why the big giants like Intel, TSMC, they are earning in billions and billions because the scaling is generating a lot of revenues and profits for them. Okay, but running at forefront is not that easy job. Huh? That's another set to look at. Okay. Okay, so I just close this. Okay. Uh, that is a very interesting chart I made recently for this VLSI conference. We just participated in a VLSI conference uh, earlier this month, and I made this and submitted a roadmap for the participants coming over there. And this talks about that how the progression of the semiconductor has happened in the last couple of decades. Okay. So if you want, you can download the set of these posters by scanning this QR code, or maybe I just copy this. Can I copy this? No, I can't copy it. I have to grab this, open the chat. Okay. Okay. So I just sent a note in the chat box, from where you can download this set of posters, where you can explain to the students that how the semiconductor progress has happened in the last 2 decades. So here, where tried to explain this roadmap, but I've tried to add all the jargons possible because many of the kids, they are not familiar with some of the jargons. So if they come across these jargons, slowly and slowly they will learn and understand the meaning in deeper manner. So here are around like 2005 and 3 and 4 around this. So we were working on the planar MOSFET technology because we were not in deep submicron technology. We were around what, like 180 nanometer, 130 nanometer. At the time, we were not in the deep submicron domain. Okay. So at that time, we were just doing a geometric scaling, which was called as, okay, or Dennard scaling era, was called as about simply geometric scaling. That means you just reduce the area by 30%, you get the benefit, everything 2x the density, 30% in speed and power. Okay. So that was easy times up then. But as the humans entered in a deep submicron, there were up new challenges for the scientists because as they were doing scaling, because that's what they have done, just reduce the size and boom, you get everything better. They understood that since this, because of the scaling, this channel is reduced so much that electrons are not able to propagate in a straight path in the channel. Instead of that, they are colliding with the silicon atoms, and due to that, the delays have increased. They are no longer an high performing device. Instead of that, they are getting very poor current results from the scaled transistor. At the time, the scientists found a solution that if we put silicon nitride capping across the gate, okay, so if you put a silicon nitride capping around the gate region, so what will happen? It will create a kind of pressure, mechanical pressure around the channel region, allowing the silicon atoms to be dispersed and a little bit displaced from the channel region. And now the electrons can propagate straighter. So that was a whole new research which concluded that this is required, plus new set of process was added in the fabrication. And hence we got a new kind of MOSFET, which was called a strained planar MOSFET. Okay. So that all started in the deep submicron region. Okay. Then, so this was till 2011 because this all started around 65 nanometer and below, especially in 32 nanometer, they hit this kind of wall. Okay. Now, post MOSFET, there were new set of transistors were introduced, which we are called as FinFET transistors, which are even called FilmFET 3D transistors. So in the next couple of slides, we'll talk about the FinFET and follow through the nanosheet. So here, after geometric scaling, we shifted to equivalent scaling. Okay, so that means where the dimensions are equivalently scaled as compared to only scaling of the channel. Okay. Later, we were scaling the channel structures, not further W by ratios, the structures which are getting scaled. So FinFET has progressed from around 2020 onwards to till now. So almost for 5 years, it has been very prevalently used. But now the nanosheets are the upcoming transistors we are going to take over from the FinFET and carry the semiconductor baton up ahead. So upcoming technologies which are complementary FET, which I will talk about in the last almost during the closure of this talk. And I'll just introduce you guys at how the complementary FET is going to take over for the fabrication. Okay. Okay, so we start with FinFET. Okay, so as the scaling of the MOSFET was happening, as we talked about, that the geometric scaling is no longer possible because how long you can make the channel so smaller that still the current can flow. The problem was not with the on current. The problem started with the off current because when you turn off the transistor, still it was so much amount of leakage was happening that billions of transistors will accumulate in huge amount of current wastage. So to challenge this issue, okay, they came across with an indigenous solution that let's grow the channel region, okay, vertically upwards, okay, and hence came the FinFET transistors. Okay, so if you see around, so here you have the gate. So here you have the gate, okay. So instead of passing the channel beneath the gate, no, it's no longer now. The channel is passing through the gate, okay. So as you can see, there are thin structures of silicon substrate which are grown and passed through the gate region, as you can see, which I'm highlighting for you, okay. So here, the gate is surrounding the channel from the three side. You can see right side, the left of it, which we can't see right now from this angle, and the top side. So these are the three areas from where the channel is covered by the gate. Okay. So this raised structure was called fins. Okay. And hence its name FinFET. Okay. Okay. So you can have multiple fins in a transistor, and the FinFET offered a much lower leakage current across the MOSFET and offered a better control of the on-off ranges. Okay. So if you take and ask me that how kind of dimensions it are possible with a FinFET, so generally the width of a nominal FinFET ranges from 6 to 12 lambda, okay, based on the technology. Length is always 2 lambda if you are working on lambda-based rules. For anyone who is not familiar, that lambda is nothing but half of the technology. So whatever technology node is there, so it's half of it. So for example, if you're working on 14 nanometer, okay, so lambda would be 7 nanometer. Okay. So obviously, if you multiply by 2, then it will become length will become 14 lambda, 14 nanometer. Okay. And width ratio can vary from 6 to 12 lambda. Okay. Number of fins varies typically from 2 to 5 because as you will increase more number of fins, obviously the current will increase, but at the same time, fabrication issues becomes a little bit critically to handle. Okay. The pitch of the fin is around 6 lambda. The thickness is just 1 lambda. And the gate length obviously will be 2 lambdas. So these are only numerical figures attached with the construction of an FinFET. Okay. And this is how the 3D view of FinFET looks like. So here what you are. So that is the gate. Okay. And you can see the drain and source are passing through the channel region. Okay. And here you can see there are 4 fins which are there. In this P-type MOSFET, you can see there are also 4 fins over there. Okay. So this is a cross section. On your left, what you see is uh, an N-type FinFET. Okay. And here you can see it has what 14 number of fins, 1, 2, 3, 4, 5, and so on. Okay. So this is if you take a cross section from this view, then this is what you see. So this is called as the height of the fin. I just zoom it for you. Yeah. So what do you see this vertical line? Okay, this is what height is called as height of the fin. Then that is the width of the fin. Okay. And moving forward. Okay. So if you ask me how, I'm sorry. Then the next question comes up that in generally in an CMOS MOSFET, the drain current is generally proportional to width upon L. Now, in this case, they are fins. So how the width is calculated? Okay. So here, this is a general formula with the help of which you can calculate the width of the FinFET. So as you can see, the fins are only covering the gate region, or it's from the top and the height. So three sides, right? As we know. So twice of the height, okay, and just you adding the width of the fin because the height, because they are touching it from the left and the right, and the third part variable, which is the width of the fin, okay. You just multiply with the number of fins you have in a transistor, and that will be the equivalent width of the FinFET for that particular transistor, okay. So this is how the generator of a FinFET look like in a software named as Microvent, okay. And maybe I just do one thing. I just take a quick demonstration for this and show you around how you can design something in a FinFET. So I just open the tool for you. I'll just check my chat, something. What is the thickness, which is lambda? Okay, I'll just show you. So here I work on 7 nanometer FinFET technology as of now. So if I click on mouse generator, so here you can see I can specify this software and I tell him that I require 2 number of fins and that will be the fin length. So you see the length of the fin is 8 nanometer, whereas I'm working on 7 nanometer. Now, that is the thing which I will talk about later because the Moore's law and the physical things are not relevant now. Okay. So the software tells you that thickness of the fin is 1 lambda only. Now, since lambda in this particular technology is 4 nanometer, okay, so hence you see that 1 lambda, which will be equivalent to the thickness of the fin. The height is 35 nanometer, and the pitch of the fin is 20 nanometer, okay, which is around 5 lambdas. So I just generate this device, place it over here. This is how it looks like, okay, and if I just zoom it, so you see this is what the fins are passing through the polysilicon across it. Now let's say I want to show you that how the fin looks like. So I'll just take a 2D cross section and cut through this plane. So there. So that is the polysilicon, which is the gate region. And these are the fins which are passing through the polysilicon. Okay. And let's say if I want a higher current from my transistor, okay, because if you go back, click on mouse generator, and 2 number of fins was able to produce around what 0.2 milliamperes, and let's say I give him 4 fins. So obviously the amount of current gets doubled. So that is the amount of current that NMOS can carry through. So these are the 4 number of fins NMOS transistor, and just take a 2D cross section from this side. So there you can see these are 4 pins present in this particular transistor. So let's take a 3D view of it. So this is how it looks like, these 2 transistors. This is what you see. So here you can see that the fins are passing through the polysilicon and joining the drain source or the other end of the channel over here. So these are the contacts or the wires which connects with the metal one layer as of now. Okay, on the top of this contacts. And this transistor was having 4 fins. So I just come across and see 1, 2, 3, and 4. Okay. Any questions you have, anyone? Okay. If you have any questions, you just drop me on the chat box and I will try to revert as and when I feel I'm like I should answer the particular one. Or I will take up all the questions maybe at the end of the session. And don't worry, I'm available over the emails. And if you have any doubts which you think you want to discuss in detail, definitely we can discuss over the emails also. Okay, just give me a moment. I just shut down this because I'm in a region. It's quite not that cold, but yeah, a little bit cold. Yeah. Okay. Now, a little bit of some introduction on some jargons related to FinFET. So this is what you saw on the MOS generator in the software I used. So where you specify the number of fins, the gate length is fixed kind of. And these parameters related to technology are fixed because generally this is the manufacturer decides that this is what he's able to manufacture successfully. The user can control only the number of fins and maybe number of fingers with the help of which he can have a varied current carrying capacity from the transistor. Apart from this, what else is there? The else is there is the type of transistors you can generate with the help of the software tool. So Micron generally offers 3 options in generating the type of transistors, okay? Like low leakage, high speed, and high voltage. So in high voltage, he just increases the length of the channel to handle the stress of higher voltage, okay? Harsh, okay, I answer this, okay? Whereas in the industry practice tools like Cadence or Synopsys or other tools, they have more than 10 device options, which are offered to the designers. That allow designers to select a very precise transistor configuration for each and every design based on analog or digital based designs. Okay. Okay, I have already shown this that generally in high density drawing styles, generally 2 fins are used because there are many digital circuits which have fixed fan outs and a very low current requirement at the input and the output side. So obviously you can design that part of the circuit using 2 fins only or with the lowest current possible. So that is called as high density configuration in which 2 fins are sufficient enough. Okay. So generally in SRAMs, etc., 2 fins can be sufficient. Okay. And 1 fin is very rarely used because fabrication is quite complicated and challenging. And uh, yes, you can design any kind of digital circuits and plus difference between the software tools I will demonstrate later. Don't worry. Okay, so yes, don't worry. So I come to the demonstration part where I just show you various kind of circuit design with the FinFET. So let's start with basic inverter. So this is how it look like. You have the symbol over here, and over here you have the P-type FinFET, and on the bottom side you have the N-type FinFET. The input and outputs are routed through here. Okay, on the right hand side, what you can see, and 3D will look like. So maybe instead of showing the gates, I just make the examples for you. Okay, let it be like this. I don't clear this layout, which I made earlier for you. So you remember that is an NMOS type transistor. So maybe I just generate an P-type transistor. Now see guys, logic remains the same. Now if you look, if I make 4-fin transistor, N-type, I get 400 microampere of current. But for P-type FinFET, I don't get 400, I get 349 microamperes. So that is not cheating because the mobility of PMOS and NMOS are different in both transistors because electrons are majority in NMOS and holes are in PMOS. Holes are less energy, so obviously less current, and the matching can be done by giving him more number of fins. So I can give 5 number of fins for the PMOS to match up all up close. It's not close because it's a little slightly higher, which is okay. I just place it on top of it and take a FinFET gates and take a metal contact, make an output node, maybe extend it for the next connectivity. And that's it. The construction is almost complete. I have to apply VDD for the PMOS over here and sub ground for this node of the NMOS. So I take the ground. These are virtual grounds. These are virtual signals. Okay. So I take a VDD supply for the PMOS over here, VDD for the NVIL. Because remember, again, logic remains the same. I must show you the P-type MOSFET. So that is a P-type FinFET over there. This is what we have seen earlier. Okay. So this we have seen it. This was an N-type FinFET. Now, this guy N diffusion is made of N diffusion. So obviously the substrate is P-type, which is reverse body allowed. Okay, great. But in case of PMOS, we need a reverse bias body. So this guy is a P-type material. This is a P-type material. So I can't have that. So in this, I have to fabricate an N-mill first, and then only I can grow an N-type, P-type diffusion. Hence, you see an N-mill around the P-type FinFET, and this is true for MOSFET and FinFET, both of them. Okay, so, and if you see in 3D view, this is what you will see. So this is what you have drawn just now. You have placed an N-type FinFET, and that is a P-type FinFET. Okay, and this is what you see. The N-well is below the fins of diffusion of the P, right? That is the N-well, okay? So if I remove the N-well, this is how it will look like, okay? They will both look similar except the color, because P is denoted with brown color. Yeah, see, more or less it's same like stick diagrams. Not 100% same, but yes. Because in stick diagram, you just mentioned the line where the W bar ratios are not mentioned. They are written. Okay, so I take a clock signal and apply at the gate. Let it be like 0.5 nanosecond and 0.5 nanosecond high and low. And this is the node I want to observe. So I just put something like V out, I know what I call it. And I'm ready to simulate this. Maybe I just press this button and there you are. Here I can see the inverter simulation. So that's why you see that high to low propagation delay is 1.1 picosecond. So that means this is because of the NMOS, right? This part is because of the NMOS. Okay. And this guy is because of the PMOS. So if I ask you why they are different, why they are not same, maybe it's okay if I place a small amount of load at the output so that the delays will increase and we can see a good difference between the propagation delays. So I take a virtual capacitance from this palette. I'll just click this button and place it on the output node, and a very small capacitance value like 0.01 picofarad, very small capacitance. Okay, so all the delays are prima facie, I mean, very close, but slight difference is there. You see, low to high propagation delay is 10.1 and high to low is 10.6. So 10 points, why this is higher? And or maybe I can just ask a simple question, why they are different? Anyone? Just to ensure that you guys are listening and I'm not talking to my laptop. That is the only one difference I find in the online offline teaching. Online teaching, it's like talking to oneself. Many of times my family members ask, why you are talking to the laptop so seriously? Okay. So anyone, why the low to high propagation delay is less than high to low propagation delay? A simple question. Hmm. I take it next time. I see someone. Different switching speed. Yes, Sanjay ji. Yes, they are different switching speed. So that is the question, that why they are different. Why they are not same. I just made an NMOS, I made a PMOS, joined them together, made an inverter. So they should have been same, right? So why they are not same? double bile ratio. Okay, double bile ratio. But kiska double bile ratio? Whose double bile ratio is wrong? NMOS, PMOS, mine, yours. By the way, I loved ATAL FDP name because firstly, I understood that the ATAL FDP is named our late Prime Minister Atal Bihari Vajpayee. Later, I came to know it is at AICT training and learning. Oh God, how what a wordplay! Capacitance in effects. Oh, capacitance effect. Capacitance effect. Okay, my question is why the delays are different. That's a very specific question. I want that only at that point the thought should be there. So yes, even I just change the capacitance by double clicking this capacitance. And instead of 0.01, I make it 0.02. I just kind of double it. So delay will almost doubles, right? But my question remains the same. I'm not asking you why the delays have increased. That is the answer is that capacitance due to increase in capacitance, the delays have increased. My question is very specific that why low to high propagation delay is lower than high to low propagation delay. The answer is very simple. I have already illustrated the answer while drawing the inverter. So I just want to check that due to difference in carrier mobility, Ramandeep ji, again, it's not on the pinpoint answer. Charge carrier electronics are faster than holes. Again, Deshmukh ji, yes, that's correct. I mean, the answers are right, but the problem is the answer is not right to the specific question I'm asking. Charging and discharging times are different. Yes, that is the question. Charging and discharging times are different. So my question is, why is the difference? Why? I mean, they are different? Uh, you guys want to see what I did while making this? Because by the time you get the recordings, that'll be a day. So you remember that I took a P-type FET, N-type FET. I made him 4 fins. It gave me 407 microamperes of current. Then I made a P-type FET and I made it 5 fins, not four. Okay. It gave me 436 microampere of current. We generated that devices and placed it, made an inverter. So that's why you can see that this have 1, 2, 3, 4, and 5 fins. This guy have 4 fins. Okay. And when I simulate this, I see that the the delays are different. So the question is again the same. Why the currents are different for the low to high and high to low propagation delay? Now, see, this becomes engaging as I see I'm engaging all of you into an thoughtful process. So this is where the thinking ability of the students also are enhanced. They develop a critical thinking skills. That what happened? Did I didn't pay attention in the class, or did sir has done kind of cheating? He has explained something else and he illustrating something else and asking question differently, or is it I can understand by his steps and find an answer that he made a transistor of NMOS with a 407 microamperes and PMOS with 436 microamperes. So both devices have different current. So obviously, whenever they are going to charge and discharge any capacitance, the amount of time they will take will be different because the currents are different. Okay. So the answer is since both devices they have different currents, so charging and discharging time constants will also be different. Yes, unequal current. That's right. And why they are unequal? That is another question. And there the answer comes up that the mobilities are different or they have different W bar ratios. And why different W bar ratios? Because the mobilities are different. Okay, coming back. Okay, so let's continue on understanding. So similarly, you can draw a various kind of layouts possible with the FinFET. So that is what we draw an inverter, and that is nano designs. Okay. For example, if I ask my software to make something in NAND node, So don't worry, it's not going to take too much of time. I just say compile a NAND gate for me, and he makes a NAND gate. So this is a very compact two-fin layout design. And explaining this will not be difficult at all. You can see that NMOS are in series. You can see that this is in polysilicon crossing one gate and the second gate. So the input comes from this. I just start drawing. So input comes from this, and it is sourced to the ground. On the top side, here the VDD comes to this transistor and also to this transistor. And this has a common point taking to the output. So that's why this PMOS is in parallel, okay, making an NAND gate only configuration. So I can attach a VDD and VSS, they are already attached. I can simulate them to make it working as in NAND gate. So I just double click on A, apply a clock, and B, I apply a clock. NAND gate, I ask him to be visible in the output so that when I run the simulation, I should be able to see the results. I just run it for a smaller time duration. So there we can see that only for 1, 1, the output is 0 when the input is 1, and over here, then the output is 0. For the rest of the time, they are different. Any questions over here? And very interesting. I mean, you can see that the W by ratios are same. So this tool will allow you to engage with the students in a very deep learning methodologies, because if you see this is W and these W, they are both same. Okay? Both have two fins, right? So that means the current carrying capacity of both the transistors are different, but because of the configuration, they will play a beautiful role in understanding. Because if you run the simulation, and if I ask you that you see high to low is 3.25 and low to high propagation delay is 1.75. And the another question is that why they keep on changing, but after a while they settle down. High to low is 2 and low to high is 1.25. So why is that? So maybe you can just write down this question and maybe discuss this later and find the answer this later. Because to find this, you have to make this NAND gate as an inverter. Then it will be really well, because in NAND gate makes it cheating, because when inputs, any input is when the both in any input is 0, the output is output is 1. When both inputs are 1, then only the output is 0. That means this guy over here. So when both this NMOS are in series, right? When they are in series, then only they will discharge the output, okay? Whereas this guy over on the top, either one of the transistors is on, either one of it, or both of them are on, okay? So that means if you know that they are just nothing but resistors, right? We all know this. They are in parallel, right? So either this is on, or this is on, or both of them are on. Now, if this guy is R and this guy is R, so either he will charge the output with R, okay, because either of it, or when both are on, then it will charge by R by 2, right? So the current will become less because both our transistors come in parallel and the current will double. So obviously, the charging time will be faster in R by 2 case, okay? So that is the thing. And there is where you can engage your students, that you see 1.75, that is because both of the transistors are on, hence 1.5, okay? Whereas 2.6, both are in series. That's why 2.6 is coming. So let me give him a good playing ground, that I just connect one of the input with the DC supply. So now what happens, this guy is always kind of on, okay? And let me simulate this. Okay. So now you see that this is kind of good, because now this is kind of working as inverter. Now in this case, what happens? One of the PMOS is on, okay? Only one, okay? Whereas in case of NMOS, both will be turned on. So now low to high propagation is 1.6 and high to low propagation is two. They are kind of almost matching, but slight difference is there because of the mobility of the PMOS transistors. Okay. So that is another thing. Uh, I don't want to go into practical side of the circuit design. Okay. Coming back to the FinFET, to yes, designing FinFET is good, but there are many of times kids make mistakes that they make non-aligned designs, and what happens? They are not fabrication ready because non-aligned FinFETs will always produce distortions and failures in the fabrication, and plus the distribution of on-off current ratio will be unevenly spaced out, which is not recommended. And this is just a slide I make and explain to the faculties also that don't accept any of the designs where students bring up to you that this is what they have made. Until they have made a very aligned and regular gate based design, you don't approve their experiments or the assignments done in the classroom. Okay. Okay, so this was prima facie about the FinFET. Now, since FinFET has already been in a market for some time, and we are about to witness something new in the upcoming market, so I thought to put my focus more on that. So, if we talk about FinFET, after running the show for around 5 years, they found that the scaling will not continue for the FinFET because growing the fins is a very challenging and complex manufacturing process. Plus, the leakage current of the transistor started producing problems because the leakage of the number of transistors are so high now, tremendously high, that leakage current is putting forward a whole different challenge for the fabrication units. Okay. And since we are almost about to touch the 3 nanometer physical limit, so the FinFET was not able to support the leakage requirements. Okay. So here we are moving towards the next gen transistor, which is about to be introduced in the market, and that is nanosheet. Okay. So a nanosheet transistor, as we see through in the presentation, so that is what was the planar MOSFET. Okay. And just now what we have seen that the FinFET transistor. So where we grow the fins above the substrate and give a three-side control of the channel. Now, the nanoribbons, or they are named with various names, or synonyms are there, we will see through. They are thin stack of sheets which passes through the channel region, allowing the gate to have a four-side control of the channel, giving them very extra and enhanced control over the leakage current ratio versus the ion current, and hence making the Moore's law survive for another maybe 1 decade. Okay. I just put it on top. Just give me a moment. Sorry. Okay. So nanosheet, there have been some trial runs, as I heard, and Intel was supposed to release this end of 2025 with an 18A, but the fabrication yields and the thermal requirements are not good enough, and they have again slowed down. And probably I've just heard some just a month back that they are dropping the 18A node and will be shifting to next one. Anyhow, so nanosheet or the Intel also call as gate all around FET, and sorry, that is the Samsung calls it, and multi-bridge channel FET, or some people also call it ribbon FET. So that is a nanosheet transistor, okay, where the scaling will be continued for the next decade or so. There is one more important thing I wanted to make clear, because many of the students and researchers, they see that the Moore's law is a linear line. The Moore's law is a very linear line. And as I illustrated that you just reduce the size of the transistor by 30% and you get a 50% area. That is no longer true now. Okay. So the Moore's law has splitted from the FinFET technology itself. So if anyone says that I'm working on 3 nanometer technology, that doesn't means that the channel length of the transistor is 3 nanometer. The actual channel length is, or of the technology node is 8 nanometer or somewhere around. Okay. So if you open my previous semiconductor roadmap, so you will also see two lines in that, where one is the Moore's law or the indicative marketing based scaling. And there is another splitted line, which is the actual physical gate length of the transistors, because it is impossible to fabricate the transistors at such a smaller scale. But due to marketing requirements and explain the users that how the scaling is happening, how the number of transistors are getting doubled, they have continued keeping this thing alive. So yes, the guiding principles again remains the same with the NSFET, that the objectives are the same, that we are working to gain space, get better speeds, and try to save more power. And only thing is that in nanosheet, this shrinking is not significantly happening. So if you see around a 5 nanometer FinFET technology transistor, if the physical length is 8 nanometer, the gate length is in 8 nanometer. So in a 3 nanometer nanosheet transistor, the channel length is same 8 nanometer. So they are not shrinking the technology. They are bringing a new kind of device with the help of which they will get the three objective possible without shrinking of the technology. So that is what they are doing it. Okay. So here they are trying to replace this in the 3 nanometer a FinFET with a nanosheet to get the same advantage of the scaling. Uh, Cell height, I just skip this part. Okay. So that is why they have the old design styles which are made with like 7 tracks or 5 tracks, which generally called as 5T, 3T, 7T tracks. Okay. So that is nothing but how much amount of design you can fit through, or how many number of gates you can fit through between the two nodes of supply lines. Okay. Now, due to FinFET's large width, this was not possible because since the three sides contact without the FinFET, they never allowed. Now, with the help of a bit smaller gate pitch in nanosheet, they can fit more amount of transistors in the same given area. So this is how they are doing scaling. Okay. So this is just a tentative explanation that due to nanosheet, the scaling down furthermore is possible. Okay. So again, industry is looking for 30% reduction in power, 50% reduction in area, and better saving of the cost. Okay. So let me illustrate some of the things with the nanosheet. Okay. So if I come back to the tool where I can illustrate a nanosheet transistor, and let me show you around how does it looks like. So just see over it. And okay, so I just again open that. I just click the same button. This is called as mouse editor, we call it. So here, that is the length of the MOSFET. Okay. And here is the width, which you can control. Okay. And in this option, this is the number of fingers. So for the people who are familiar with fingers, fingers are nothing but the multiple number of transistors which are adjacently placed apart, so that you can save some area in having multiple parallel or series transistors. So coming back, so let's say this is the default value 8 by 16 nanometer. Now this is, you see, this is 8 nanometer, whereas I selected a technology node. If you look on the bottom of the screen, you see that you see a number which is 3 nanometer. So I'm saying that I'm working on a 3 nanometer technology. So that means the length of the channel should have been 3. No, that's not true now. It is 8 nanometer. That is the minimum amount of fabrication I can support. So 3 nanometer is a marketing or a Moore's law number, whereas the physical gate length remains 8 nanometer. So I just generate this device, place on the board. So if you look closely, it just from the top view, it looks like a simple MOSFET. Okay. So that is my gate, and the green one at the back is the diffusion. These are the metal lines on the top and going extended towards top and bottom. And the white cross you see is nothing but the contacts. So I just shift this. And if I take a 2D, and just draw a line vertically downwards from the gate. So this is what I see. Okay. So this is the polysilicon, the red one, what you see. And these are thin sheets which are passing through are nothing but the nano sheet, which are passing through the polysilicon. Now, this guy, the gate is surrounding the sheet from all four sides. So it's not three sides in case of FinFET. It's not one side as in the case of MOSFET. It's surrounding the channel from all four sides. So it'll have much higher enhanced control in the leakage current and even the on currents. Okay. Um, I just cleared the gate. Ah, okay. Mm. So if you ask me for a 3D view, this is how it look like. Okay. So that is a polysilicon. Okay. And the red one, and you can see the sheets are passing through the channel. Okay, so these are the contacts and these are the metal one lines which go up above. You can ask me a question that why there are two more polysilicon lines on the right and left. Anyone would like to ask this question? Or you say that yes, you know the answer. If I want, I can enable the top and bottom also. So on the top and bottom are also polysilicon layers or some blocks are there. These are called as dummy kits or dummy blocks. So these are just to improve the manufacturability of the MOSFETs. Okay, because due to etching process and the chemical etching out process, it is possible that the main gate can be wiped out very easily. So to apply a kind of brake to the vapor extraction, these walls are erected all around the FETs. Okay. I will come back to the tool as and when I feel that I can demonstrate something more to it. Okay. So Intel has already demonstrated this Armstrong era, which is Intel is commonly calling it. That is Intel 20A. 18A is no longer probably in production. I captured this image some time back, and probably Intel is dropping 18A. Okay, yeah. So I just move this bin. Now, sometimes this is very confidential. That how many number of nanosheets, because I can control the width of the nanosheet in the tool that how wide I want it, with the help of which I can generate or increase or decrease the current carrying capacity of the transistor. But the question comes up that how many layer of nanosheet I can have. So in the software tool, you can always have a fixed number of nanosheet layer. I can't vary that from transistor to transistor. It will be fixed all around the node. So Intel has demonstrated Intel, TSMC, and Samsung. They all of them they have demonstrated that they are going to put up three layers of nanosheet device. So probably that is what we have gone through the three number of nanosheet in the micron software also. So because this information is collected from the release notes of these manufacturers, and generally it's not easily available. Okay. This I've already explained that the pitch and the deviation of the 3 nanometer node. Okay, so that is what let's say if you're working with 3 nanometer node, so in that case it is the lambda is 4 nanometer, so it's not 3. Okay. Okay, so I've already captured the cross sections. So if you take an MOSFET like this, it's just a white background image and take a cross section between A and A dash. This is how the nanosheet will look like. So that is the width of the channel. Okay, so that is in the sheet. Okay, sheet width and the sheet thickness. They are two important parameters related to the nanosheet. That is very easily understood. Okay. And you just take the surface area of this, multiply with the number of sheets you have, and you get the equivalent width of the nanosheets. Then a manufacturer can allow the design tool manufacturer or designer to have multiple types of devices like slow versus fast device. So in case of slow device, it will have less number of width. And if you want more current, that will make the device faster by giving it more width. So if I come back to the tool and demonstrate this quick illustration, and I just say that, okay, I want a 32 nanometer width. So obviously the current will increase of the device. And if I place it over here, so here you can see that the width is much more higher as compared to previously made device. And this transfer will be faster as compared to this one. Quite understood. And this is how it looks like in 3D. Maybe I should have done that in showing the software that I just zoom out, say 3D. Yeah, this is how it looks like. So these are dummy gates on the right, left, top, and bottom. The center one, what you see is the actual polysilicon gate. This is the actual one. And there you see 3 nanosheet passing through the channel region. Okay. And maybe I should make both of transistors for you and then join them together and make a simple device. So I keep the same 32 nanometer for N type. Again, 397 microamperes. I put it on the board. And again, MOSFET generator, select P type. So instead of 397, it becomes 356, which is very obviously we know that due to mobility. And we just place it on top. Okay. So I just take the metal one, join these metal one, and maybe extend on the right. Take the gate, join the gate only one. Put a VD for the PMOS and VSS for the NMOS, and put in square clock. Apply the gates. And this is the node I want to observe what comes over here. And select this. So yes, uh, it works in inverter. The delays rising for almost of the same order because the currents were quite similar. And for the lower current, they are generally at the same range. If you add a capacitance, then only changes. Do I see some problem in the software that because for the PMOS, I don't see an envelope there. What went wrong? Okay, what's wrong? What's wrong with there? So this is what we have done, right? So this is the metal one. We joined it, we extended on the right, and that is the N-type device, and that's a P-type device. Where is the anvil? On the bottom side, there should have been an anvil, right? For the PMOS, only an anvil is there, right? That's what we have seen in the books from so long. Maybe I just remove this. I delete this block so that I can see 3D view nicely. I just take the gun. Yeah. So I remove those blocks, the dummy gates. I see that there is no anvil. That is the best part of the nano sheet, that you don't require anvil, because anvil was required because you need to have a reverse body for the p-type material. Now since you are growing on the top of the substrate and passing through the polysilicon, you don't require an anvil type, so there is no polarization required for the nanosheet p-type transistor. So that reduces one of the steps. So that's why there is no well, no polarization required. Okay. So there is no need of separate and well contact. Okay. So this is how you can make a simple inverter. I have done it in a different way. The illustration is different. So generally, you can fit in the nanosheet transistors. They allow 5 metal track design pitch. So that is a very compact design style, and the amount of number of tracks which you can fit between the VDD and the ground, okay, that is only called as amount of metal tracks you can fit it. So you can have a 5 metal track pitch as compared to 7 metal track in FinFET. So that was significant reduction in the size. Okay, this is what we have already done. I've already shown this to you. And yes, the amount of metal layers, it goes till a standard 8 metal layers. And generally, as you go higher on the metal layers, as we know, that the resistance increases, and they are generally used for the longer and heavy current supply as compared to local routings. So generally, the metal one layers, they are used for local routing purpose, and whereas higher metal layers, they are used for supply lines. So let me illustrate this part. Um, Okay, maybe I just compile something, a simple design like this. That is a three input NOR gate. So in this case, what is happening is if you see the 3D view and zoom out, so that is a metal one layer. As you can see, that metal one connects this part to the other part on this corner. Okay. And that is metal one over here also for the supply lines. But if I wish, I can take a metal 8. I can take a metal 8 layer, okay, and draw something like this and try to connect this by extending the metal one. Yeah. So what I'm doing is I'm trying to give him a power supply line from the 8th metal layer. So if I zoom out, you can see that the contacts are placed between all layers. So you can't, as we are all aware, that we can't go from 8th uh, floor down to first floor. You have to pass through all the floors. So similarly, all from the 8th metal layer, you have to have 7, 6, 5, 4, 3, 2, 1. Then only you can reach the ground floor. And you need the metal contact at each and every point, and the width and sizes also changes at each layer. You can see here the contact is smaller, bigger, bigger, and bigger and bigger as goes above, because the resistance increases and you need to give him more space to carry that amount of current down below. So this is what you can illustrate to the students in very easy manner, and that is how it looks like when you make a contact. Okay. So these are some of the examples that that was made. Okay. So that is a ring oscillator, three-stage ring oscillator, and that too, uh, three loading inverters. Okay, three in parallel. So this is how it look like. Let me see if I have it, or maybe I can illustrate that in the second half, where I will be illustrating things in the practical types. Okay. So this ring oscillator we compared with the publications which were available in the market, on, I mean, on the publishing places. Okay. So if we see around the red one, what do you see? These are the from Skyward 2019 and 20 and papers from the Ahmed. And our results were quite closely matching with the same ring oscillator results mentioned by the publishing papers. Okay. So these are some of the basic gates with the NAND NOR and OR gates that you can draw using the nanosheet. So let me open them for you and show you around that how they will look like when you will draw them. So I just open the example folders. There are numerous examples that are available with the help of which you can explain stuff to the students. This is 3 nanometer technology node. Yeah. So these are three gates like NAND 2, NOR 2, three input NOR gate, OR gate, and AND gates. So all of them are available here. Okay. So if you want to see a 3D view of it, so this is how it look like. Okay. So this is the metal line. What you see, they comes in 3D alive. Okay, these are the like contacts and joining metal lines to joining together. It becomes cluttered. I can remove the metal lines and see through below the metal lines. The gates, the nanosheet, which are passing through the polysilicon, N-type and P-type, both of them. Okay. So if you want to simulate, see the results. So it's very easy and quick to simulate since all of you are very familiar with the functioning of these gates. And so that is what you can make use of this tool to illustrate deeper to the students that how these gates function and how the layout can be made. And that is another thing that you can always engage your students to design a layout which is much more compact and optimized than this one. This becomes a very engaging exercise because there is one thing which most of the teachers do, that just complete the assignment, you see the results, take the printout, go home. I try to do the other way around. That, okay, you have made it, that is good. Now try to do the same layout, try to fit in a much more smaller area possible. Now the real experimentation learning starts. Okay, because now many of the students, I see that this is what they do. They go to the lab and they just click this 1, 2, 3 button, and this is what they have. There's a NAND gate available. Okay, I say that no, no, boss, try to fit in into much smaller height between these VDD and VSS line, and the amount of area that you are wasting, try to optimize as much as possible. Okay. So there, the real learning comes up. Okay. So there are numerous examples which are available made on using nanosheets, like the basic, what you have already I've shown you, this gates, flip-flops on the latches. Okay. And even the memory cells. So that is only, I think I collected this from made by students. So still a possibility optimization was possible because some area was wasted. Okay. And if you want to see an optimized layout, this I would prefer and recommend that this is much more compact implementation of SRAM cell. Okay. This is some again student project I collected to illustrate. Okay, no problem. Yes, another thing is that you can always engage students to something creative. So yes, there was one question someone asked that what DSH can do. So for that person, I don't remember the name. Sorry for that. Just pay attention for that. So with DSCH, you can construct a lot of circuits. For example, I can just drag drop any kind of gates which are available in the library. So that is the library. For example, I can just drag drop buttons, multiple buttons. I can just right click and start making connection with the inputs, and I can put an LED on the output. Okay. And simulate this. I can say I can illustrate very easily that which nodes are going high and low. So for 1, this carries 1 and some is 0, but that's okay. And similar way, I can make a lot of circuits. For example, uh, any particular one anyone wants to? Um, okay, let's make a simple toggle gate. Um, so I just drag drop and button for the reset, a clock signal node for the clock, and connect the input like this, and take a feedback from the Q to back to the OR gate. Okay. So I apply reset, the Q goes 0, and as I make the enable 1, you can see that the flip-flop starts toggle because that's an XOR gate. So when you apply logic high to one of the input, it starts working as an inverter. Okay. So if this is 1 and the previous input is 0, then the next output would be 1. And when 1 comes, the output becomes 0, and so on, the toggling will happens. So similarly, you can keep constructing many examples. So as I took that example of a counter, so I pick up the same example from the library. There are numerous and numerous examples through which you can illustrate a lot of things to the students. For example, count till 9 or count till 16 counter. 16 is good. So let's take this. You apply reset, and you can see that as I remove the reset, it starts counting, and it'll count till 16 and roll over, fall through. Or if you want something else, you can just add a break and make him count till 9 only. That's a BCD counter. BCD counter will do that. He just matches this when it becomes 9, and it becomes 9, he applies a reset. So you can see there is an OR gate in the reset on the bottom side. You can see this one. So that is the reset. Okay. So he gives reset to this guy. He clears the flip-flop against, and this guy counts till 9 and will roll over. Okay, 9 and it goes 0. So maybe I can just ask him to convert this into a Verilog file. So what he does, he converts into a gate level netlist of primitive components like AND, XOR, DREG, etc., and places this at this location, which is the installed location or the example location. Now what I do, I want to tell to my students that design that counter. That is two ways. First, the functioning and working, where I explain them. I compile Verilog file, go to that folder where it was, microInt DSCH examples, and it was in counters. Yeah, count 9. Yeah. And say, just compile. I'm not taking you through complicated process. And there you are, that the layout is ready for the counter. And I zoom on in this area. Okay. If you find it difficult, you can also use a black and white background where I find it comforting for my eyes. And you can see in the reset, I can double click on the reset. I apply a pulse because reset cannot be a clock. Because if you apply a clock, it will reset the flip-flops continuously. And here I can apply a clock. It's like almost 1 nanosecond low and high, which is okay. I just click on the simulation. Maybe I just increase the step size so that it goes faster. So here you can see that this is LSB, the next one, and next one. So this is like 0010. So these are four outputs: 0010, sorry, 0010, 011, 100, and 101. And this is 6, and this is 7, 8, and this is 9. So on the 9, you can see that he generates a small pulse because as it becomes 9, that AND gate triggers, it generates a pulse, and as it makes 0, the pulse again goes back to 0. Okay, that's why a very short pulse is observed. So yeah, it works seamlessly as in counter. I can do lot of analysis of this, that how much amount of static power consumption is there. I see this is the active power consumption, which is almost in the first simulation run, it was 13 microwatt. In the next simulation window, it was around 15 microwatts. So in and around total average of 14 microwatt, I can say that this counter is consuming. But what if I just open the clock and apply ground to it? Now this guy stops toggling. This guy stops toggling. So this will be the power which I will see drastic drop. So this is 7.4, but there was initial toggles which were in the power on. So around 7 microwatt is the power consumption of this device when the clock is not toggling. Okay, 7 microwatt. So you can ask your students to optimize this design further even. Okay, try to make thing which is much more lower power. Plus, you can see that there is a lot of area wastage in this design because there are a lot of metal lines, and this was extended too long. So it's a very the aspect ratio of the design layout is not that great. Students can be engaged into a lot of activity where they try to fit in into a squarish layout or aspect ratio of 4:3. Okay. Okay. So it's almost like 8ish, which is a time of break. So maybe I just hold on for a minute and take up a couple of questions and see that everyone is alive over here. And uh, if you have any questions, and otherwise we take a break of a minute or so. Is that okay? And continue.
Yeah, it's already like 6:30 we started.
Yes, ma'am. So it's okay.
Yeah.
I think I just take up some
Audience poll,
questions.
5 minutes. We can take a break.
Uh,
Mm,
We'll keep connected.
Hello.
yeah, we keep connected. We keep the session
Yeah,
alive.
all
We
of
don't
us will keep
discontinue
connected.
it. Yeah,
Yeah.
we don't do that.
Hello to all
And
the participants. I have unmuted to all. So those who having the questions, they can raise your questions. Mr. Vinay Sharma, sir, will answer your queries.
yeah, I'm here. I also just take a minute break.
Yeah. 5 minutes is okay, I feel. We'll keep connected. We'll be back by within 5 minutes. Good to hear to get the feedback. Please continue, Yogesh sir. But then let's take break for everyone.
Okay, so while everyone comes back, I can take some questions. Abdullah ji, Sadullah ji, there are many videos are there. I will share all the resources. Maybe tomorrow I will compile all the resources. I will share across with all the participants. Don't worry about this. Okay. Anyone else who is present over here and wishes to discuss anything about till all the rest of the participants take their break? I'm available here for taking up any questions.
Sir, good evening, sir.
Yes, ma'am.
Sir, this microwin tool is it's a free tool, sir, or any licensed tool, sir?
It's a licensed, ma'am, but the fees are so nominal that the comparisons can't even be made because it's a very cost-effective solution.
Okay, okay. Shall
Yeah.
we optimize the power by using this microwin tool, sir? Shall we design any digital circuit using nanosheet or GAFET?
Yes, you can. Yes, you can.
Okay.
There are a lot of papers available. That's what I will share. I will compile it. I'm sorry, actually,
Okay.
honestly, I'm on vacation right now.
Okay,
So
okay, sir.
I'm not regular on the laptop. But tomorrow morning, I will compile a package for all the participants. Don't worry. And I'm
Oh,
also planning to share the evaluation copy of the software license. So during the
okay,
end
sir.
of this workshop, I will share that.
So in the future also we'll mail you, sir, whenever we are doing any work. Actually, I am the researcher,
Okay.
scholar.
Uh-huh.
I am doing on the nanosheet only.
Okay, ma'am. Great. Yeah, yes, certainly. You can stay in touch
Okay, sir.
for any of your questions or issues. And we sponsor a lot of research scholars across the globe. So anyone who is coming forward with an innovative ideas and doing something welfare of the engineering, we support them.
Okay, sir. Sure, sir.
Yeah.
Mhm.
Hello, participants can ask the questions.
Actually, there are many questions in the chat.
Okay.
Vanessa, if you scroll up, I can just.
Madam, you can read the questions one
Yeah,
by one
yeah,
also.
yeah,
No problem.
yeah. Can we design any digital circuit using?
Yes, yes, you can.
Yeah.
Most of the digital circuits are possible. For the all student UG PG levels design, this is all possible in microwind. Just take off my coat.
Then one more question I find is what is fin thickness, which is lambda?
It's one lambda, ma'am.
Yeah.
I illustrated that.
Then another is what is the minimum thickness of SiO2?
Again, I answered that because that is changing with every technology. So from couple of nanometers to multi nanometers is possible. Okay. Shall I start? I think it's almost 5 minutes now.
Hello, sir.
Yes, sir.
The first session is really enriching the knowledge of participants. You have explained
Okay.
different concepts like CMOS, FinFET, okay, nanosheets. Now I have one question: how researchers are going to see FinFET and nanofits for their own research? Okay, what
Okay.
are the different topics are available for the research for researchers or the faculty members?
Mm-hmm.
And what are the different tools available for the simulation for the same? Because at the end, you should have the simulation tools for the validation.
See, now there are a lot of research which is done that with the give, because see, many of time research is possible because how much amount of currents are possible with the scaled transistor. So with this amount of current, if I design a circuit layout which is uniquely placed and is computing or giving me the same performance in a lower current, then my paper can be accepted or the idea can be accepted.
Correct.
So now the micron offers, because this is so low cost and the design cycles are so fast, then he can research and implement the iterations of many papers possible. Okay. And he can find his own ideas possible. And the results are accepted because the amount of current, on-off current proposition which is there in micron FinFET or nanosheet is there, that is at par with other tools which are available in the market. Okay. So in that way, the results will be comparable. So faculties can take research in various kind of circuit layout, optimize the performance, or design some unique architecture of the circuit. Or now the fabrication side, it won't be possible because Micron will not support directly the FinFET fabrication or the nanosheet fabrication.
Correct, correct. So that's my question actually.
No.
After you have to fabricate and then validate what we have designed or whatever the results we have got.
Correct. So it's better that the simulation results that which are accepted would be at the circuit level. If you propose that this is the kind of adder I've designed using only, let's say, pass transistors, and the current will come down, yet the performance are comparable or manageable. So that is acceptable because, for example, I recently saw one paper done by some student in Bihar. He made a 3 transistor XOR gate in a FinFET. Okay, so generally an XOR gate requires minimum 6 and a standard practice is around 14 or 12. This kid made a XOR gate using only 3 transistors. Now this is a very explosive idea. I mean, to do this, a very risky thing to do. But yet he went ahead and showed the result. The delays were much more higher, but the area optimization was tremendous. So obviously his paper was appreciated a lot.
Okay. Okay. So thank you for your valuable input, sir.
Most
Okay.
welcome.
Now we can move to the session 2.
Shall we continue?
Yeah.
Okay. Maybe I'm actually I'll wait for a minute and then I start.
Okay. Okay, sir. No problem.
Okay. List of topics on which students can do projects. I'm thinking, Sanjay ji. I'm thinking. Um, uh, it's numerous. And I would say that whatever project students do, they should do it on their own. And you restrict, if they are working on micron-based design or
Mostly.
UG
Mhm.
projects, then restrict them to 50 to 100 transistor design.
मला नाही का ते वरचे लोक बघा ते त्या साठी ते जिओचा तो गळ्यातला बेल्ट नाही घालायचा
हम्म.
त्या कंपनीमधून एक माणूस आलता आय कार्ड वगैरे काय नव्हतं गळ्यामध्ये.
Hello.
Yeah, yeah. Yes, sir.
No participants.
Okay. I think, shall I continue? If any one of you says that I shall continue now. So I start.
Yes, sir. Yes, sir. I think it's 8 o'clock, so we will move to the second session.
Okay. Okay, so far we have just I explained about that we progress from FinFET, MOSFET to FinFET, and then the nanosheet. Okay, so let's see that what is up of the line in the coming couple of years. Okay. So very immediately you will see that the next coming node, which is around 20 angstrom, which is 2 nanometer node by Intel. In fact, they have already placed in the market, but probably you won't see 20 nanometer coming immediately. What you will see now, the next node which is upcoming is 14 angstrom, or which is also called as 1.4 nanometer. Okay. So in this case, Intel is trying to gain a total benefit in terms of density and performance by changing the whole play field by introducing two revolutionary concepts. One of them is buried power rail, they call it. The Intel call it buried power rail because in the existing line, what happens is this is the existing nanosheet or you can say FinFET technology implementation. So that is my substrate layer of the wafer. Here I have the devices, are the metal 1, 2, 3, 4, and onwards. So generally the VDD VSS lines are on the top of the layer and they are routed on the top layer. Now, due to this, what happens? There is a lot of stress. One, two, the thermal stresses are very higher. Three, it's very complicated to have place for the lower interconnections of the network. So instead of that, Intel is about to introduce the buried power rail. So what they are doing is now the supply line, which is there, the VDD bases, that will be delivered from the back side of the wafer. So that will be not from the top of the wafer. Instead of that, it will be coming from the downside. Okay. So this will have more increased cell density. They'll have reduced supply resistance. The entire wafer on the bottom side will be only available for the backside power delivery. So you can have much more compact designs of nanosheet transistors. So this is a 7 nanometer, 7 track, a 24 nanometer pitch or 190 nanometer pitch of the FinFET design. So in case of 2 nanometer or maybe 1.4 nanometer nanosheet, you will have only 5 tracks. So this would be much more compact as compared to the nanosheet. So this is how it look like. So this is a simple device, or you can say this is what a NAND gate. Okay. No, this is not NAND gate. This is NOR gate. Let me see. Just let me mute the voice. Okay. Where is this? Okay. So again, no.
Okay, sir, I have muted. Okay.
Thank you. So that's a NOR gate. So if you take a cross section between A dash and B dash, so A dash will look like this one on the left hand side. So you have the PMOS and NMOS, they will have the buried power rail on the bottom side of the silicon. And this is how the plane will look like. And huge giant metal contact structure will be constructed beneath the wafer to deliver the power supply line. Now, this is whole challenging because so far the substrate or the wafer is always processed on the top of the layer. Now processing on the bottom side will be a real challenge. And Intel has already demonstrated this technology in 20 angstrom. The only thing is that the production line, the yield were hit and bottleneck, and they have just to catch up with the TSMC, they have discarded their 20 angstrom and even 18 angstrom node, and they are jumping directly on 14 angstrom node. Huge risk Intel is picking up. I hope and wish them luck that they succeed in fabricating the technology nodes as they have mentioned. So this is what you see, that this is the NOSFET layer. Okay. And this is what the buried tungsten through silicon wires, which will be placed to connect with the backside power delivery. And the substrates are quite thin. I mean, this part will be only 0.5 micrometer thick. So challenges are real. Okay. So maybe I just illustrate this, and this is how the captured images, because after the post presentation, you might refer back. This is how it looks like backside power delivery. But those people who are online right now, I will show them and demonstrate how does this look. Now, this is not available in the latest version of the microRun. So this is an upcoming feature that on which we are working right now, and we are about to close and release. This is next version of microRun software in which this will be demonstrated. So I just compile something like an inverter. So here you can see that this is how the inverter looks like. Now, what you see over here, there's a PMOS nanosheet and there's an N-type FET. Okay. And these are the contact layers on the output. As I believe everyone must be familiar with this kind of construction. And this is an contact connected to second metal layer and to take it to the output node. So let me illustrate the 3D view of this. Yeah. So you see this one, So this is, I'll zoom it a little bit more. So these are the nanosheet transistors. Okay, so that is the N type and that is a P type, and you can see that they are passing through the polysilicon. This is a metal contact, and the metal 1 layer over here, and that is a metal 2 layer on the top. Now, what is interesting is this. You see this one here? So that is an N diffusion, and there it goes and contact and takes it to the substrate layer on the bottom side over here. So that is a backside power delivery of the supply lines. This is for the VDD, and that is for the ground. That will be delivered from the backside of the substrate, and this is what it look like. Okay. So that is something which we'll see in future. So if you see this, I double click on the input, apply a clock, say this should be visible in simulation. That is inverter node that is visible in simulation. I apply it to it and say simulate this. So yeah, it works quite well. And then I need not to apply VSS and ground because they are delivered from the backside. Okay. And rest of the logic of the inverter will remain the same. Okay. Coming back. So what do you see backside power delivery that which will be available in 14 angstrom node or 1.4 nanometer technology node? That would be probably available by end of this year or maybe at the max early next year. But the real question is that what next? I mean, what after backside power delivery? So Intel, TSMC, they both of them are working on a next generation node and process technology, because as we have already established this fact that shrinking the channel is not much further possible. So it is only possible to give benefits of scaling by offering novel designs and better technology as compared to just geometrically scaling things out. Okay. So next technology things which you will see in the coming times is the stacking of both PMOS and NMOS on top of each other, which will be commonly referred as CFET, complementary FET transistors, CFET. So you will have the polysilicon, which will be common for both of them. Okay, and I just take this. So that will be common for both of them. You can see the polysilicon is common. The N type will be on the bottom side, the P type will be on the top side, and both of the transistors will be stacked on top of each other. And obviously, you will carry forward the buried power rail or the backside power delivery. Okay, and this will allow the 3D growth of the silicon on top of each other, and it will be totally a new design approach for the upcoming nodes up ahead. So this is what it looked like from 10 angstrom. This is expected on 1 nanometer. And probably under this era, we will enter into femto second scale. So right now, all of the designs, what you saw just now, the delays are in picoseconds. Okay. So, but now this point onwards, the delays would be in kind of femtoseconds. So obviously, things will be much more challenging in uptime side. But as humans, we have solved numerous amount of challenge and obstacles in our life. So obviously, I don't see a much of problem as up ahead. So this node is expected by around 2020. We have already implemented a prototype. I'll just show you this. Okay, I'll just show you that. So what I do is I just restart the software and load the 110 Armstrong technology. Let me compile something, or do I have to compile, or this will do? Yeah. So I just do a NAND gate. Okay. Okay. So what do you see here? So let me make that. Okay. This is not good. I should have started with inverter, so that understanding is step by step. I should not rush things. I start with an simple inverter. Okay. So what do you see here? Do you see a PMOS and MOS? Earlier we used to see an NMOS over here. We saw an PMOS on the top, but nothing over here. Okay. So you see something like a brown diffusion over here and a green diffusion on the bottom side, and that is in common stacked area. So let me show the 3D view of this. You see this one? So here, that is the N type, right? So here the backside power is delivered to the N-type diffusion. Okay, this is the VDD line, and here you can see the power is getting delivered to the P-type MOSFET on the top side over here. This one, what do you see? This one. So that is getting delivered to the top side P-type MOSFET. Okay, what next? And here you can see the N and P both are stacked on top of each other. Okay, only thing is that this is L-shaped so that it can connect to that power rails. So here you see on the center side, this one, here you have the N and PMOS stacked on each other. Okay, over here. The only thing is that you see something else, because here this is the N and P stacking on top of each other. And on the bottom side, that is the NMOS which took an L turn so that it can connect with the backside power rail easily. Okay. And if you take a 2D view of this and do a line between, this is how it looks like. Okay. So that is a backside power delivery contact. That is a stacked PMOS and that is an NMOS. Okay. So shall we simulate this? I just double click on this, apply a clock and say maybe slow a little bit. And that is the node. That is VDD. This is ground. Yeah. Call this one node. Okay. Maybe not connected. I think I have to restart. Yeah, this is on the prototype stage. We are still working on it. Yeah, this is in. So there should be a clock. And this is node 4. Yeah, this should be visible in simulation. And okay, no, this is not connected actually. Yeah, there is some issues in connection. Maybe I just do an VDD over here. Let me see if it will work. Yeah, this is okay. Yeah. Yeah. So this works in inverter, and you see the delays are in terms range of femtoseconds. So very interesting time side. So definitely the AI is going to get benefit out of this technology, and we will see rocking revolutions coming out. The correct wave is around 10 millimeters in the case of grid. Only the buried power rail is changing. 10 millimeter. No. That's probably for the MOSFET you're talking about. Okay, we discuss on this. Okay, so this is an illustration that we have just made in the software. We have tried to keep the GUI of the software as intact as possible because we now want our clients getting retrained on the change because of the change of the layout. Okay. So let's talk about the scaling, a little bit of it, as we have seen in the last some time that how we have progressed from MOSFET to FinFET to nanosheet to upcoming complementary FET and even the buried power all the way down the road. So we just see across that what happens when you scale it and why we scale it. Okay. So first thing first, that scaling no longer is carrying the same lines. Okay. So now the technology and the gate length, they used to be very strongly correlated. For example, earlier days in, let's say, in 180 nanometer or 0.18 micrometer or 0.12 micrometer, when you used to scale, it was always geometric scaling. And generally the 0.12 micrometer, if you used to say anyone that I'm working with this technology or I'm working this using this node, so the gate length was also 120 nanometer. But today, it's no longer relatable. As I mentioned this and discussed this earlier. So starting around 20 nanometer with the FinFET, when the Intel demonstrated the FinFET first technology node, So kind of the physical gate length and the Moore's law, they are all moving in a different line. The only thing is that the scientists are trying to align both of the objectives, that is better density, better power, and better performance, by introducing novel devices and the novel design techniques to get this thing possible, or the Moore's law's objectives possible. Okay. So that is why with the novel devices, we saw FinFET nanosheet, that is all possible because of that. And novel design, that means the CFET and stacked buried power delivery. These are all novel design ideas which will allow the scaling benefits to continue. So yes, the objective remains the same with the transistor scaling. You are trying to make it smaller, faster, less power consuming, and obviously you are trying to make it cheaper. Cheaper for the manufacturer, because obviously he's interested in keeping the profits and margins. And yes, he passes some share to the clients by reducing the cost with every gen CPUs or the products they fabricate. Okay. So more or less, this remains the same. So if we take up a lineup, for example, from Intel Core i7 CPU I pick up, okay. So whenever you buy in the you go in the market and buy a CPU. Let's say I want an Intel Core i7 CPU. They mention that this is 14 gen, 11 gen, 12 gen CPU. So does that mean the architecture has changed drastically? No, the architecture remains the same. It's only the nodes that they change it. So for example, the Gen 1 was manufactured on 45 nanometer. By the way, I still have that CPU. And just to mention as a nostalgia part, I'm a very die-hard collector of CPUs. I have my own collection of starting from the third CPU made by Intel, that is 8080A, and onwards, 8085, 8086, and till what I can say, Core i7, this one. So, and so you can see the number of threads and cores more or less remain the same till nanometer era. But let's say if you take a 14 gen CPU, it has whole lot of cores and threads. So obviously they are even adapting the architecture also. But once the architecture is adapted, generally with the next gen, it continues the same, only that they take the benefit of the scaling. Okay. And obviously, they have recently released a new CPU architecture, which is Ultra series. So apart from CPU, although they had a GPU also, which was a kind of primitive one, they have introduced an Intel Arc CPU and GPU into that. Along with that, they have also added a neural processing unit. Since we all are living in an era of AI, so there are many laptops which will be now edge enabled. They call it like edge enabled devices. So any of the software who can take benefit of the NPUs available on board of the CPU, your laptop, your processing can be much more faster and higher. So obviously, that is all possible because of the scaling of the transistors. But many of the students, I grill them on this particular slide that let's talk about, discuss about how the challenges have been changed in the scaling. Because if we talk about scaling challenges then and now, because then means that around a decade or maybe 2 decades back, so the scaling was done to cut down the cost, right? To get better revenues and better margins. So what has changed today? I mean, is the scaling done with some other objective? No, the scaling today also is done just to get better profits and margins. Okay, so that you can manufacture more number of chipsets in a given wafer area and can double your profits. So yes, the prima facie thing remains the same, no changes in that. But then earlier, around 2 decades back, when we were in a kind of geometric scaling era, so scaling was done just to make the performance better. But today, it's no longer scenarios. We are in such an era where the materials are dominating the performance. Okay, scaling is not driving the performance. These are the materials who will allow things to be better. So that is why I always take and illustrate to the students by taking an example of two cars from the automotive industry. Both of them are racing cars. Okay, this was maybe used in racing in 1960s, okay, or maybe 50s, and this is used in today's Formula One racings. So both of them, they illustrate a classic example of design process, okay? Because scaling also kind of illustrate a design thought process between the IC manufacturing. So here, earlier days, if you give a better, more powerful engine, the speed will go up. Okay. Now, this is no longer relatable to this car. Even though I give him more powerful engine, probably he will not go faster because now it has hit the roadblocks, dynamics, or the physics of the air drag, okay, airflow, or the physics are much more challenging at that speed what the engine can drive it. So no, so here the materials are driving the performance. Now this guy has to be lightweight. Here everything was made of wood and iron. Here everything is carbon fiber. So material have entirely changed the way the car can perform in the racetracks. Okay. And then in earlier days, it was all about performance constraint. The the chipsets, if you guys, anyone over here who is probably of my age or maybe elder than me, if you remember that in late 90s, Intel and AMD were they racing around. Every chipset they release in the market, both of them were claiming that my chipset is much more faster, 100 megahertz, 133 megahertz. One guy said 240 megahertz and 500 megahertz. And they people were waiting that which guy will go above 1 gigahertz barrier in the market. And if you remember, even around what, maybe 5 years back, anyone who used to go buying a mobile phone, it was checked that how much frequency is the marketing gimmick. You remember the mobile phones maker, they used to label it that my mobile phone runs on 2.4 gigahertz CPU. The other guy said my CPU is 2.4 gigahertz. Someone said my CPU is 2.5 gigahertz. So at that time, the performance was kind of criteria for everyone. But today, no. If you buy a mobile, which is 2.5 or 2.8 gigahertz, but let's say it runs only for a couple of hours, you will buy it? Well, no, no. Today, it's more power constrained. So people want, yes, they want a performance, obviously, but the performance now is a kind of out of the benchmarks, right? So today, people are looking for more power optimized design as compared to the performance. Now, this thing is related to the next line that in earlier days, the active power consumption was in the kind of dominance. That means the designers put focus that when my circuit is operating, then I should consume as less as possible. Okay. So that was earlier times. Today, it is all about standby power. We are no longer focusing on active power consumption because active power consumption we already brought down and significantly in the control. The focus more is on standby power. It's something like if you take off example of a car, then I can closely relate to something which is called as. Are you guys familiar with fast tags? I believe every car of yours must be having an installed sticker of fast tags, right? So what is a fast tag? Fast tag is an NFC enabled sticker and that you install on your windscreen. And whenever you pass through the toll, without waiting for longer period of times, you just pass through the tolls. Now, how does this is related to standby power? Now, if fast tags are not there, okay, what happens on our toll plazas? There are thousands and thousands of cars will accumulate in few minutes if the gate is not getting clear in few seconds, right? So imagine there are 500 cars waiting to cross the toll and none of them shut down their engines, isn't it? No one turns off their air conditioners. They keep the car going. So obviously, imagine thousands of cars waiting to cross the toll. They will hugely waste a significant amount of fossil fuels just to move a couple of inches. So that is as comparable to standby power. Now, since today's chipsets, they have billions and billions of devices. So imagine if everyone is leaking a 1 nanoampere of current, so that number will accumulate into a huge figure. So obviously, the standby power is into dominance in design consideration. So that is a very prominent figure to control. Then in earlier days, the scaling was totally independent of design process, geometric scaling. I mean, need not to take care about that, what and how you are scaling. Okay. And the fabricators and the designers, they always sit separately. They never will be united because totally independent design process. But this is just like similar to this. This guy, if I have to, someone says that, okay, in 1960s, I want a faster car, just put a bigger engine, right? Or maybe do something with the tires and I can make the car go faster. But today, in this case, you can't do that. I can't have a just, I need to know the people have entered to the material level physics of the material used in the tire, the material used in making the fiber body, and even the drags of the design of the car. So it's an entirely collaborative design process as compared to earlier days. So scaling has brought down many changes in the design aspects of the chip process. Another interesting thing. Generally, this is I keep it for the students. This is a very interesting slide of mine, where I talk to students that how what changes scalings can be done, because this is an exercise I ask them to think on. That imagine you are an design company, let's say Qualcomm or let's say MediaTek or any microchip or any company. You are head of that company and what you can imagine if you were in 90s, okay, if you are in like mid 90s, what ideas you can think of, okay, what challenges or things you should adapt uh, due to scaling progression. Okay, so generally students think on this, they answer that sir, scaling can become complex, how can design thing. So after discussing and debating and understanding that what students knew about the scaling process, I introduced them that how the EDA tools or the industries they popped up due to scaling. Okay, all thanks to scaling. Okay, so if you focus on this and come back, so one of the prima facie industries that popped up was the IP core design companies. So as all we know as a teachers here that we know that IP cores are nothing but black boxes, intellectual property cores. These are kind of products which can be used in designing a final product. Okay. So IP cores industries, they popped up hugely in late or mid 90s or and today also there are many companies which are flourishing because of the IP core only. The companies like ARM Incorporation, uh, they make the IP cores, and the companies like Qualcomm or the MediaTek, they make use of their IP cores and design the final product. For example, the Snapdragon processor that we use in our mobile phones, that is designed by ARM Incorporation and made by Qualcomm. So it's in collaborative effort. And now what happens, many of the students, they are not familiar with, sir, what is IP core? We don't completely understand. Can you make some small or easy example for us to understand what is IP core? I see a question coming up. Okay, feedback. Okay. So what I do, I just take them to next slide and I explain them what is IP core. I explain this that if you have an SoC system on chip, so there are multiple blocks on that chip, and it's not possible for one guy to design the entire block sets. So IP cores are nothing but a product made by someone else you insert in your final product. So again, many of the students did get confused that still we are not able to clearly get an idea what is an IP core. Then I take this example. So this is an example of an IP core, right? So let's say my friends are coming home in the evening and they said, "Okay, Vinay, you cook a very good pav bhaji, and can you make a pav bhaji for us in the evening?" So I said, "Why not? Please come over." And the problem is that I need the masala or pav bhaji masala for making that bhaji for all of my friends. Not bhaji, bhaji, yaar, sorry. Okay, I don't know what I was thinking to write this. So uh, now if I have to make that garam masala for the pav bhaji, so I have to go to the market, buy all the spices, grind them, filter them, and maybe saute them, and again process them for to be used in the my final process or the product, which is pav bhaji, right? Not even pav, only the bhaji, right? So what I do, I just go to market, buy a ready-made pav bhaji masala made by this gentleman or his company, MDH. Okay. Now, this is a soft IP core because this is intellectual property of someone else. So this is not a final product. I cannot eat directly. Can I eat this pav bhaji masala? No, I can't, because this is like not a final product, but can be used to make your product. Okay. So you just take software, make a pav bhaji masala product and serve it to your friends, and there you go. So that is nothing but a soft IP core. Why it is called a soft IP core? Because you're allowed to make changes in the composition of his pav bhaji masala. I can add a little bit of spices to it, or maybe add a little bit more of chili powder to make it more spicy for my friends. Okay. So since this allows some changes, that's why it is called a soft IP core. And this product itself is called as IP core because it is available off the shelf. It's tested, is validated, and it is accepted. Plus, it is low cost. Okay. So, what are other flavors of IP core? Anyone else? Anyone else know what other kind of IP cores are there? Obviously, if there is a soft IP core, so it's quite obviously that it's good to have also an hard IP core. So if you ask me what is an example of hard IP core, I give this example to the students that there are a lot of this kind of ready-made packets are available. My friends call me this time. They didn't choose and pav bhaji. They asked Vinay, you make a lot of good butter paneer masala, and we wish to eat that. And we are coming over in half an hour. Just prepare that. Now, since the time to market is very short, I don't have enough time to prepare the recipe. I just go to the market and I pick up this ready to eat IP core or product from some this manufacturer. I just heat it up, add a little bit of flavor or maybe garnishing like of a butter, serve it to my friend, and my time is saved. So this product is ready to use. Hence, this is called as hard IP core. And similarly, in IC also, there are a lot of IP cores available which can be ready to use. So this is a silicon proven design of a high performance build, which is readily available in the form of silicon, which can be inserted in your layout and directly used and connected with your design. So that just saves one thing, the time. Okay, that's a time saving component. Okay. So IP core is a product or used to make a final product, and hence they are licensed at some given cost to be allowed for a number of uses or number of instance uses, depends on the agreement made by both the parties. So coming back to the graph, so many of the companies, they saw that since the number of transistors are doubling every 1.5 years, so after some time of frame, they will see that they saw that and predicted even that it's not possible for any one company to design all the blocks of the chipset by their own. So obviously, they thought that why not we start designing these kind of IP blocks and start delivering them. So hence many of the industry companies flourish because only of that scaling exponential they saw in the market upcoming. Okay, so like and Texas Instruments is also there, and there are many companies who are only making IP cores for their end clients. Now, since scaling progressed, another challenge which was interestingly faced by the designers, which was logic optimization. So in early 2000s, the designers saw that because in earlier days they used to designing using schematics and a little bit of HDLs. So HDL was not that deeply penetrated in the design industry. So they predicted because of the scaling that's no longer possible for designers to write in highly optimized code. They made mistakes and the logic was poorly defined. So hence they designed optimized algorithms which was highly appreciated by the industry, and they became a permanent part of the tools. And in earlier days, they were tools and software and algorithms which was paid and licensed, but later they become an kind of an integral or necessary part of the software, and they were no longer charged, and they become a standard. So with the scaling, another challenge was faced, which was the physical limit, which was also called as layout optimization or the physical optimization. Now, what happened is that when you design a chipset, let's say you design something like this and do something like that, uh, cascaded gates interconnected to each other. So earlier days, the delays of this logic was, let's say, 3 nanoseconds or something, and the delays of the interconnect was 1 nanosecond. So here the gate delays was much more higher as compared to the the wire delay. Okay. But as the scaling continued, what happened was that the wire delayed remained very similar to the old days, the wire delays, and the gate delays, they became much more smaller. Okay. So now the gate delays became smaller than the wire delays. So designers face another challenge that I have a lot of gates now to optimize. Okay, I can have more gates, but try to reduce this wire delays. Okay, so here this was called as physical optimization, where the designer faced a challenge to optimize the wire delays. Hence, there was a huge requirements of manpower who can optimize the layout as per the physical needs of the delays. Okay. And with upcoming AI ML, they are huge, tremendous changes which are coming due to scaling. Now we are getting edge devices, and now we are seeing a lot of separate ICs which are available in the market, which are edge powered. So they are getting attached to our existing products like CPUs and giving birth to revolutionary products which we are going to see. So this was all possible due to scaling part only. Okay, I already illustrated this IP core logic. Okay, so yeah, opportunities. I think we all from academic circuit, most of us, and we are already aware that the semiconductor ecosystem in the country is up and rising. So India is heavily boosting the semicon infrastructure in the country. We already have a Tata plant upcoming, probably by the end of this 2028 or 30, the chipsets would be published, or it will become a production ready. But we have to prepare the manpower, because there are a lot of companies who are coming in the design. There are a lot of companies coming in the fabrication. So they are all looking for a skilled up talent. Okay. So what's up for us? Obviously, our job is to prepare better talents who can be taking this responsibility of growth of the semicon infrastructure in the country. So another question comes up: how to scale up? Yes, it's something which we can discuss for hours and days and long. So the problem is that our UG infrastructure is very tightly capped. Not every student is ready to take up the VLSI subject. Okay. And plus, since being a semester-based system, we get hardly in 20 hours of practice time to teach students the practical skills of the subject and generate his interest first. Because many of the students, I have seen that they get scared with the subject because, sir, this is very difficult. I'm not able to understand the concepts. Can you please go slow or maybe illustrate it much more deeper? So I find students difficult in grasping the concept. Okay. So, and plus, this is all we are familiar with, because the funnel which is there, which prepares the students and make them into engineer. So obviously, one of the roadblocks is the semester-based system, where he has to study the subject in which he might not be interested, and he has to still score sufficiently to keep his grades up above. Plus, the kind of resources available to the students are very limited. Plus, the subject related to VLSI are very limited in terms of UG curriculum. And obviously, this funnel is heavily pressured due to job requirements, doing better, distraction from their social media platforms, and obviously the time which is distracted due to the many activities, extracurricular activities happens in the college days, which are important, I believe so, but should not be extended too long. Too long. So yes, I have seen that many of the curriculum, they are very well designed. That there's a digital VLSI subject which is there. We study the digital subject second year and advance this into HDL and FPGA and CPD platform. That's very good. There is also some part which is analog design. and both of them are connected through a simulation blocks so that they are able to become a better problem solver. And only for the students who are interested, they can climb up high and picking up the advanced topic, which will make them better critical thinkers. Because the industry is not looking anyone who can just explain the full form of wage deal, and they are looking for people who can solve the given problems and who can think in a proper format. Okay, because I've seen students who just get zapped while they are asked or thrown any question. That is because they become zapped because they are not able to think critically on the subject. Now, the critical thinking comes up by knowing the design theory which you take up in the classrooms. Now, knowing the design theory and practicing, these are two separate things. Okay, because for example, you can know about a recipe of cooking a pav bhaji, but unless you have not cooked yourself 5 or 7 times, you cannot say that I can cook a very good pav bhaji, right? So practicing more and more will allow them to become confident. And plus, if you add projects to them, various projects apart from their routine curriculum of the experiments, that will prepare a better critical thinker as compared to a normal student. Okay, that is why I always say that, because in many of the colleges and places, there are dronacharyas available. I know that there are a lot of good teachers are available. So the students are blessed with good resources. They have software, they have learning materials, and they even have very good mentors to teach. So yes, they can produce very good Arjuns, and they should be doing that. But there is another way of learning that I call it equitable way of learning, right? So that comes with only one way possible, that practice as much as possible. Now, practicing requires the student should be able to learn on its own. He should be able to practice on its own. He should be able to guide himself on his own. So that is only possible when the tools, even the simplest tools which are available, through which his learning curves are small and easy. So that's why I call as less our students that try to practice more and more. So that is for VLSI and doing hard work. So just an introduction, nothing more than that. And I think there's some question. No. Okay. I won't be talking. This is on the slides. I've kept it. I won't be talking officially on the product. Okay. Maybe I just do a demonstrator. I just explain all the technology nodes, and this PPT would be available to all of you, so you can go through all of that. And I will take that. I will just demonstrate one of my example that I do for my students. Okay, I do it for you and illustrate that how the learning can be enhanced. Okay. So generally what I do is in my illustration with the subject, I illustrate the scaling to the students, that how the technology scaling has happened, and try to teach them the various benefits of the nodes like MOSFETs to FinFET to nanosheet. Then later I introduce basic gates and explain the interconnect design, try to teach them better design strategies, that is introduction of the PMOS and MOS and the VI characteristics and the layout optimization even. Because for example, if you see on the screen, that is an two input NAND gate, okay, on the left hand side, and that is another two input NAND gate only on the right hand side. Now this is a perfect cell made by a group of students, which is much more optimized and which can be routed much more efficiently as compared to the first one. So this is in bad design, and this is an, I would say, a better design as compared to the first one. So such kind of exercises can be illustrated to the students much more easily. That's what I do with the software. Okay. And once they are comfortable, I illustrate them much more complex blocks like VCOs, ADCs, DACs. So I try to always go beyond the syllabus which is mentioned in their curriculum. Okay. So maybe I just illustrate at this point of time. I just illustrate this. Okay. That what I try to say this. Not this one. I don't need you. Okay. So shall I do a MOSFET technology, let's say? 90 nanometer, just on the edge of the deep submicron, 90 nanometer technology node. So just pay attention, please. Anyone, if you have doubts or question, immediately you feel that you are stuck with some question and you want to put forward in my demonstration, you can just place in the chat box, and I will try to answer that during this session. So just pay attention in this session. So that is a practical side. So I illustrate what you can do with the software and how you can go beyond the normal curriculum. So what I do is I try to grab students that how the CMOS VLSI layout is easy and what kind of stuff you can do with the layout designing. Okay, I see a question coming up. No, okay, not this. So what I do is the first thing first, I try to illustrate that how you can take this in lambda. This is 2 by 2 10 lambda n type, which is 443 microampere of current. I try to make an inverter first. Okay, I just put in p type. Okay, so since p type, I took the same W by ratio 2 by 10 lambda. The current is kind of almost half. Instead of 443, this is 276. It's somewhere less. Okay, I don't need this one. So what I do, I just take the MOS gate. I join the gates. I join the metal lines. I join the metal line lasers and extend a little bit. So that becomes an inverter. And what I do now, I take a VDD supply for the N well and VDD for the P type. I take a ground for this one. And maybe I extend this MOSFET a little bit. Yeah. And apply a clock to this gate and make it slower. And take this visible node, assign it. So that makes an inverter. Okay. So this works great. I try to explain student that why low to high propagation delay is 3 picosecond and high to low is 1 picosecond. Okay, so because the drive strength of both the transistors are different. The PMOS is 290 something and NMOS is 443. Now since the NMOS has more current, so obviously he will pull down the output much more faster as compared to PMOS. So PMOS is 296, so he takes a little bit more of time to charge the output. Okay. So this is what I tell and illustrate to the student. Now, those students who just want to complete their assignments, who are not interested in VLSI, who are not interested in taking this subject, take the snapshot or screenshot of this assignment, write the power figure, understand how the inverter works, and go back home. The job is done. But now for the students who are interested, I tell them that, boss, this is not a good design. Now, since the rise and fall delays or low to high propagation delay should be matching, so how you will do the matching? So obviously the answer comes up after a lot of discussion with the students that the current should be the same. So since this is 443 microampere, as you, if you're not able to see, because probably this is, the Zoom must have shrink the current. So P type is 276. Maybe I just match up. So around at 16 lambda, I get 445. Not 100% exact, but yes, very closely matched. So I will do. Can I have 100% matching in the lambda based rules? Anyone would like to answer this question? Simple question. That can lambda based tools can give me exact same current values? Yes or no? Simple answer. Anyone would like to type if you're not sleeping? Sorry for that. Yes, you cannot have the same current because it is a lambda based tools. So the grid, what you see, the dots on the screen, what you see, there's a lambda. So that is lambda grid. So lambda is half of the technology. Okay, so right now I'm working with 90 nanometer by 2. So my lambda is 45. So that means the tool will always allow me to jump by 1 lambda. So either I can make 1 lambda up or 1 lambda down. Okay. So for example, I can have 16 lambda or I can have 14 lambda, so 15 lambda. So if I select 15 lambda, I am 417 microamperes. But if I select 16, it is 445. I cannot have 15.8. I cannot have that. So that is the drawback of lambda based rule. Now, even though if you do a nanometer, you just multiply lambda by that nanometer. But for example, if you just select 10 lambda over here and make a nanometer, so since 1 lambda is 45, so 45 into 10, 450 nanometer. So that becomes 450. Okay. So you cannot have 465, or sorry, 465. You cannot have that because the software is writing over 465, but he will generate 10 lambda only. Okay. Because he will round up to the nearest value and will show you the current value. Okay. He will never give that. So that is you can say a drawback is that they are accurate, but they are not highly accurate. Okay. Yes. Thank you, Professor Jayashri and Pranjali Deshmukh. And yeah, this is my inverter. So we try to match up the current. Let's see the simulation. So if I just go more, yeah, they closely match around 1.6. Maybe I just put a small capacitive load to see the impact. So adding a little bit of load increases the delays, which is okay. But I see the delays are quite closely matched. So it's now 17.2 and 16.9 picosecond. Closely matching. Okay, the inverter works. Okay. Now what next? I see that as I increase capacitance, if I make uh, I double the capacitance, so I should see an almost double impact. So instead of 16, I have almost like 32 picosecond delays. Okay. So obviously, as you will increase capacitance, the frequency will change. Okay. So if you see the frequency, so right now it is 1.2 gigahertz. And if you just reduce back, so this is like 16.9 delays. Okay. 1.3 gigahertz. Okay. Oh, since because the input gate is same, so the frequency will not be hardly impacted. So, okay, now what next we can make? So I can do one thing. I can just remove this capacitance, this, and just extend a little bit. Yeah. Because I want to demonstrate to you that what I can do is I can just go to edit and say duplicate and duplicate 3 times in X and 1 time in Y. So what he does, he just duplicates the inverter, and I just take a stretching option. I just stretch and short the end wells. So what will happen, the same VDD will be copied to all of them. Now what I do on the top, I take the metal one line and draw the VDD line like this. So what has happened now? This VDD will be shorted to all the PMOS transistors. Okay, now what I do on the bottom, I short the VSS line. Okay. Now what I do is I just right click over here and say connect layers. So what it'll do, it will short the input output node on the inverter. Or also input output nodes are shorted. Then I take the metal 2 and go back straight from the outside and right click over here, say connect layers. Right click here, say connect layers. Okay. And take and delete node and delete the clock. Yeah, because the clock is not required now. So what I made, anyone? So what I've just made, I just say this is the V out. I'm sorry, so what I have made just now? Anyone? What I made just now? What kind of circuit we have made right now? I just want to see you that how many answers I get. What we have made just now? Why metal 2? Why metal 2? We have made inverter. No. There are 3 inverters. So if you know that, oh, no, this color is not great. This color, okay, the yellow color. So this was one inverter. So this is output connected. So this is second inverter, output connected, second inverter connected, and I joined back on the first one. So what is this? What do you call this? And why metal 2? Yes. So what do you want me to do this? Three inverters connected in series. Yes, three inverters connected in series. So that makes a ring oscillator. So it's just a simple, if you connect three inverters like this, okay, so that becomes, sorry, pardon my drawing. So that becomes a ring oscillator. Okay, so if I run this, what will happen? This guy, let's say this is at 0. So this will be 1, 0, 1, and coming back to this again 0, and keep on toggling forever. Square wave generator, not exactly. We don't call him a square wave generator because of some things. Okay. So if you want to see in 3D, this is how it looks like. So what I've done just now, so this is an inverter first, second, and third one. So these are the metal line one I use for the VSS, and this is the metal one line I use for the VDD, and was my inverter output. So you see, this is my inverter output of the second stage. It goes to the input of the third stage over there. You see on the bottom side, shall I annotate? This is on the bottom side, connects with the first stage, second stage output. So now the third stage inverter output, either I would have used metal one, but you see there is a lot of density of the metal one on the between. So I would have taken like this, gone like on the back and coming back over here. So there would have been a huge wastage of the metal one layer. So instead of that, I took a metal 2, I took a shortcut and went through the second floor instead of going through the first floor. So that's why I used a metal 2 layer to draw a shortcut. Okay. So some chat start putting okay, first input. How okay, Premananj, I believe you must have seen the 3D view right now. So if you're not happy with the 3D view, what you can do always is double click on any of the node. So you can see the highlighted part, because many of times students don't connect layouts properly and they miss the layout. So here you see that the VSS is connected. I click on the VDD, it is connected. So this is the output of the first inverter. They are connected. You can see this one. So this is connected and the output is connected to the polysilicon of the next. So that means the gate is connected, and I can check up ahead. This one, this one. So the output of second is connected to the input of the next one. Now this is the output of the third. That is connected, shorted, right? Now becomes this one. I have to enable this thing. So this is the output and it goes back to the input of the first. So that's how they're connected. Okay. Okay. So I just start simulating. Now there is no input. Obviously, as you power on, start oscillating on its own, and it'll oscillate till it dies. And you see that the frequency is around 28.2 gigahertz after settling down. So there are these power on hiccups or the power on delays, which is okay. So if you just run it for a couple of nanoseconds, after that you can say that the free running oscillation of this is 28 gigahertz. You can call it a square wave oscillator also, but there is a problem with the square wave oscillator. What is that? It is that yes, ring oscillator. Servants are thank you, and that if you add a small capacitance to its output, it will start losing its frequency. So let's see this. So I just go to analysis. I say that I want a parametric analysis. I want to see the V out, and I want to see that what happens when I change the frequency from 0 to 100 femtofarad in a step of 10 femtofarad, and I want to see the frequency of the node V out, and I say start analysis. So this is where I can talk to the student that what happens over here. So, or maybe I just do it at a smaller gap, and small steps that I just change from 0 to 10 femtofarad in a step of 2 femtofarad and ask him to show me the analysis of the frequency. So as I increase capacitance, you can see the frequency of oscillation is getting down. You remember it was 28 gigahertz when the 0 femtofarad was there? So that is correct. So as the frequency is decreasing as the capacitance is increasing. So obviously the frequency will come down because the delays will increase because as the capacitance is increasing. So I talk to my students that there is a problem that I have a ring oscillator and I can't control its frequency. If anyone puts a small load, the frequency will change. For example, I just take a virtual capacitor, place it anywhere on this output or anywhere in the middle also, it doesn't matter. I just put in small 001, 0.001 picofarad. So remember it was 28 gigahertz. Now it uh, came down to 25 gigahertz, right? So that's not good. Frequency will keep on changing. So if I'm running any circuit onto this, any design onto this, it will always have a variable frequency of oscillation and things will not stable out. So what do I do? What to do? So I need a ring oscillator who can one thing can give me a stable frequency. Okay. So I just put that question and I put a pin to that question and place it on the side. Then what I do, I illustrate to the student that there is another kind of circuit and that is okay. So another thing is that I explain to them about the VI characteristics of the devices. So for example, there is an NMOS over here and I place it in NMOS and I want to explain the VI characteristics. So there it is. So in the tool itself, I have this plotter with the help of which I can just draw the VI characteristics in which I can see what is the width of this device, length of this device, which is 90 nanometer. I just put it on the top side. And the width is 1 micrometer. So I think this is what you illustrate also in your classrooms, that these are the curves of the MOSFET for the VI, okay, ID versus VD. So what I do, I make use of few more things of this tool that I explain to the student what will happen if you increase the gate voltage. So as you increase the gate voltage, the current will increase. Okay. So you see a dot moving up and down. Okay. So let's say the dot is over here, somewhere over here. Okay. So that is a dot. So obviously, as you increase the gate voltage, it goes into saturation at the point you leave it. So it is a drain voltage decides it will be linear or in cutoff, okay, or saturation. So if the drain voltage is less than the VG minus VTH, so obviously it will be the linear region. So that's what you see. This is what you see and draw. It's refreshing because of the, I think, Zoom platform. So you can see the animation part. So as I'm moving up down the stroller on the right hand side, which I have, I can see that the device goes in the linear or in the saturation region. Okay. So I can make some illustration to the students and see that if you increase the VG, it goes in saturation. Okay. So what happens due to this is I can open a layout which we call them a current mirror. So if I connect and two NMOS devices like this, I apply a reference voltage over here. Okay. And apply input voltage here, something like this. So now what will happen, whatever the reference current this guy is having, this guy, the slave transistor will be always be clamped to the same range of current. So this will always keep it less than reference current. Okay. This guy. Okay. Obviously less than this because obviously if the V in it is also controlled by V in. If V in is 0, so obviously the current will be 0. There won't be any current flowing through this transistor, right? This is grounded. So if they are same W by ratio, the same amount of current. And we call this circuit as, I tell to my student that we call this circuit as current mirror. Okay. So this guy mirrors this current, and if this guy is having 2W, then this guy will have twice of the reference current, because the W by ratio proportion is twice. So this is in 5 minutes illustration. I share it to my students, and what I do is I even open and current mirrors layout for them. So this is nothing but the same. You can see the gate and drain are shorted. Okay. And the same node is connected to the gate of the next stage, slave transistor. And this guy is attached to a reference voltage. And here I apply a varying triangular waveform like this. Okay. A triangular waveform is applied so that I can see rise and fall of the current passing through this transistor. Okay. So to simulate this, what I do is I simulate on layout. So as you can see on the screen, I just increase this. Sorry. So here you see a dot over here. If you are able to see, there is a dot over there, which is static over here. Okay, I've just highlighted that. So keep your eyes on to that. So I have selected N1 node, N1. And when I simulate this, I see that this guy is fixed to a value of current 25 microamperes, which is correct because that's what the amount of current that this guy carries through himself. And let's see what happens on the N2. Okay. So now I select the N2 transistor and simulate. So now you can see that this guy remains in the same zone. Okay. As the drain voltage increases, the amount of current increases to this transistor, but this guy is always limited in a range of same 25 microamperes. Okay. So that's how the current mirror works. Okay. Now what next? Now I tell to my students that you remember ring oscillator? This was a design that we made. We took a ring oscillator and shorted like this. Okay. Now the problem was the problem is as I increase the load capacitance, anything like this, the frequency will come down. Okay. The frequency will come down, change. Now, why is that? Because the amount of current this guy can sink and source is fixed. It is fixed. I can't change that. So I want to change that current as the capacitance increases. I want to decrease that current as the capacitance decreases. One way of doing that is I change the W by ratio. But again, that problem remains constant. I cannot change W by ratio on the fly, correct? Once it is fabricated, it's fabricated. So what I can do, I can just simply add a throttle to it. Yes, there's someone wants to add it. No attendance. Okay. So what I do is I do this. So this guy has an NMOS, PMOS inside, right? So I do this. I do this. So there is an NMOS, PMOS inside, right? You remember that? An inverter has an NMOS, PMOS. So the NMOS which is there on the bottom side, I add a current mirror and I add a current mirror for the PMOS also. Okay, I add it for the PMOS also. Now what happens? I can always change this reference voltage which is connected to the both, I can always change this reference voltage. So what will happen? This guy will decide that how much amount of current goes inside the inverter and comes out of the inverter. Hence, I can always control the frequency. It's just like the accelerator of the bike. As you increase or decrease the accelerator, you can change its velocity of the oscillator. So I just generally I design for them, but due to time constraint, I just open this something and show it to you. So you see, this is a layout. This is how much. This is like 24 transistor design. Okay, I can see how much of the area, etc. it is extracting. So if you look closely on the middle side, please, if you look closely on the middle side, that is nothing but a set of PMOS and MOS. So this is a 5-stage ring oscillator. Okay, so that is a PMOS transistor on the top side. That is the NMOS transistor on the bottom side. What do you see? They are all uniquely and same looking things. Then what? Then what do you see? This NMOS is connected to the another NMOS device, which is acting as a current mirror for this. So whatever the current output is there, it will be draining through this onto this VSS. Okay. And on the top side, there is another set of same current mirror, but P-type. Okay. So this guy decide how much amount of current is injected in the ring oscillator. So by just changing the control voltage over here, you can decide how much amount of current goes in and out of this oscillator, and hence you can always have a variable frequency of this. So as you can see, the control voltage increases, the frequency of oscillation increases, and as the control voltage decreases, the frequency of oscillation also decreases. So you can have an engine and who has a throttle control. So as you increase the throttle, the engine will ramp up and will give a higher velocity. And if you slow it down, the velocity will come down. Okay. And obviously it has a range that frequency minimum and maximum, because obviously things starts working after only the threshold voltage. So till the threshold voltage, you don't see any action. After the threshold voltage, you see a cutoff. So such kind of things you can illustrate to the students very easily and in a very comforting manner. You can see that in a half an hour, we less than 15 minutes, we have designed an oscillator and voltage control oscillator that we have designed, which is a professional enough. And you can always take this to a higher level for the students and ask them to design something more complicated, like okay, this was 0.12. It's okay. I think it should work in 90 nanometer also. We can design something more complex and illustrate more complex to them, which is like an whole lot complicated PLL, phase lock loop. Now, this is something which you might take hours and hours to explain and illustrate that how they are designed and why they are designed. But here I have illustrated this in some very short amount of time, and that too not drawing too much. So what we just opened right now was this part, this block, which was called as VCO, voltage control oscillator. Now I want to lock it to a particular frequency and oscillate to a particular frequency only. Okay. So what I do is I take the feedback of this VCO, give it back to a device which I can call as a phase detector, right? That is nothing but over here, you can illustrate by in your experiment that this is nothing but, kids, this is an XOR gate. Because XOR gate works as a comparator, XOR, or maybe you can make an XNOR gate. Okay, XNOR gate. Because XNOR is 1, it's 0 when the both inputs are same, right? When inputs are 0, 0, then output is 0. Sorry, output is 1. And when it is 1, 1, then also output is 1. So when the both faces are 1, the output is 1. Otherwise, it's 0. Or you can take the alternate part of this, which is XOR. Right now, we are using an XOR. So whenever both inputs are different, the output is 1. Else, it is 0. Okay. Because I want to accelerate. See a question. I share this with software. And so here, what is there? I illustrate to the students that this is an XOR gate. And I zoom to this area. Now you remember that, okay, I will not go in detail that what kind of construction of logic is there in XOR gate, but certainly I can identify this part. If you focus your eyes onto this part, so that is a PMOS VDD and the PMOS somewhere output. It connects to the NMOS, okay? It goes through one channel only and gets down to VSS. Oh, and that is the input, which is common to the both gate. Oh, I can identify Oh, this is nothing but an simple inverter. So if this is inverter, this is something which is called as width. And the distance between this drain to source region, this is called as length. So the question comes up that usually the length is small. It's 2 lambda generally, right? You see, this is 2 lambda over here. The rest of the XOR gate is 2 lambda. But here on this inverter, the length is something multiples of lambda. So as we know that the current is proportional to W by L. So if you will increase the length, the current will come down significantly, right? So just keep this in mind. We'll talk about this. So I keep this question floating to the students that think on this, that why this inverter particularly is designed to keep the lambda of the length so big. The length is so big. Why? So coming back to the pedal, so this is our VCO. The VCO frequency is given to a phase detector. The phase detector gives some differentiating pulses. We put a simple RC filter over here. You can see a resistance and capacitance. So this filters high frequency noises to something stable signal like this. Okay. So I don't want to see any oscillations over here. So this capacitor filters those signals, and this is given as a reference voltage to the throttle. And this guy works as an PLO. Okay, I share that. Don't worry about the software. So let's simulate this. So see, this is an illustrative teaching because one way is that just design an inverter, CMOS inverter, NAND gates, and show me the plots, stick it on your assignment and go home. Now, when that student will land up on an interview and he's trying to, the interviewer asked, what will happen if I increase width? What will happen if I increase the length? And what happens if you design an current mirror? What will increase the width ratio of the current mirror? Or why the VCO will happen if I increase the load? And how you can control the frequency of the VCO? Such kind of questions when the grilling will happen. Now you decide which student will succeed. Someone who has done such illustrative learning on such kind of platform where he can practice, he can open all the examples which are available in the example folders and see for himself that, boss, how much I want to learn. So that student will have a higher chances in getting a job placement because he has improvised his skills. So okay, I don't annotate and explain because the time is coming to an end. Okay, so I can see that the frequency is fixed, or maybe I can go to frequency versus time simulation and reset this. So here you can see the frequency starts increasing, and after that, it's stabilized to 3.61. So I'm able to generate a fixed frequency generator, and that to a good square one. So around 3.64, 3.62, 3.63, something, that is what I get. So it's up to you how many amount of jargons and illustrations you want to teach to your students. You can ask that, what do you call something like this? If any frequency which is around 3.6, 3.62, 6.63, or 4 even, what this phenomenon call is. So you tell them that this is nothing but something which is called as jitter. Okay. And then you ask them, kids, this is in a VCO and it has an unacceptable jitter. Maybe you can tell them that I'm not happy with this kind of jitter. This is in tens decimal. I want in ones decimal or 5 decimals accuracy, and just go and try to change the design and try to improvise the jitter. So again, they will scratch their head, maybe Google it, find some answers, circuit layouts, and try to find an answer to it. So such kind of students will always have better chances of clearing the interviews. Coming back to explanation, you can tell your student that this inverter was having a higher length because they want to have less current. They want to have less current. Now, why less current? Because since this guy is a phase detector, it's a phase comparator. So if, let's say, the difference of two inputs is such thing, so obviously there will have a sharp pulse over here. So if this guy gives a sharp pulse to this VCO, so obviously his frequency will increase drastically. He will jumps quickly. Okay. So obviously, sudden changes will never allow this VCO to stabilize properly. So any difference of the pulses like this, if any difference are there, it will not generate this kind of pulse. No, it will not generate like this. It will have something like this, a slow changes, a very slow change, so that the increase of throttle happens slowly and he catch up the frequency. So this becomes easier for you to illustrate such concepts to your students. So yes, you become your mentorship should be comfortable. Your efforts in mentoring to the students should be minimized so that you can make your students much more better skilled up. And obviously, when the students can have such kind of tools and they can go back to their labs, and apart from their 20 hours schedule time, when they see that this software is so easy and comfortable to learn, they can practice more and more circuits. And since the resources from YouTube, etc., they are filled up with a lot of information available, they can always skill up to the next level. You can, I just copy this for you all. You can download the software copy from here. And since there's also a licensed version available on the internet, but that is for the student purpose only. I'm not sure what this is. And yeah, from here. From this link, you can download the latest version of software that I have just used to illustrate for you all. And what you can do is, or you can even scan the QR code, both are the same. And once you install the software should generate such kind of machine ID. It'll generate something kind of machine ID like this. He'll pop up a window for you. So just copy that machine ID and mail to Yuvraj sir, and he will collect all the machine IDs and will mail to me, and I will share back the license with all of you. Okay, and you have to just copy that license file to your installed folder location. So generally it is C microwind or wherever you have installed it, you just place that full license file and the software should work. And you use it, you go to YouTube, you will find a lot of videos. I have also my own channel, not necessary to like and subscribe. I'm made for the kids to understand such concepts, and that will help you to start with the software. So I kept some time to answer some questions or any doubts, or you want to discuss anything from my presentation on and off or whatever I know about. So yes, VLSI is spacing up and the graph is exponentially up on rising. And the issue is that our UG and PG programs, they run very slow to allow students to catch up all the concept possible. So obviously we have to speed up. So with such kind of platform, the speed up becomes very easy and you can allow your students to practice more and more in their labs. Okay. So that is what I tell to my students, that attending classroom is not enough, because in classroom only knowing will happen. It's just like you read an recipe to make a pav bhaji, but unless you don't practice in your labs and you don't practice it hardcore by your own, the learning will never come. Okay. So learning always happen in labs. So sir, so far looks like the next 10 years is secured, because scaling is because you remember around what, like 15 years back or 17 years back, the people were asking the same question, that how long the Moore's law will prevail. See, honestly, the Moore's law is no kind of like relevant today, but the scaling is, because around 2 decades back, people used to say that we have reached what, 180 nanometer technology node. We will never cross the deep submicron. That means we will be never able to enter less than, I think, 100 nanometer. Ab kya hua? Okay, I don't know how many, because I see many participants non-Hindi guys. So now what happened? Like, so we entered in 90 nanometer. People said, no, no, this is not possible. That you have just touched the deep submicron. You cannot fabricate anything below 90 nanometer because that's so small. But the scientist continued. So now this is what actually the Moore's law is in reality. It is not a law, it's a statement of pride for Intel, because Intel carried the baton of Moore's law for so long. So it was a matter of pride for them that despite of challenges and opposition mentioned by the people, we continued the scaling. But yes, due to failures in the last 7 years, they lost many important customers and their management made a lot of mistakes. They lost the race of the FinFET scaling. The TSMC is is the leader now, but eventually the Intel is getting up now. And let's hope with the 14A node, they might reclaim their throne. So scaling will continue, sir, because obviously FinFET came up. We thought that this was never possible. Nanosheet came up, which we never thought that was possible. CFET is down the line, and definitely that is going to change the playfield. And even though the 3D stacking of that silicon die is a thoughtful process. So thank you everyone for giving your time. I appreciate a lot to all of you, because sparing time out of your busy schedule and yet coming down to online, sitting for 3 hours or a week program it is, and keeping learning. Thank you to follow all of you, because you are showing a commitment to make the VLSI education better in the country. And I am committed myself. I try to do as many sessions possible on and off, so that whatever I can share whatever is possible, so that our country can do better for the next generation. I have shared my email address and mobile number. So if any one of you have any questions, please write to me email. I will write and reply, but not immediately, because I'm on vacation right now, and I will resume office somewhere in mid of February. So certainly I will answer whenever I get time. Don't worry about that. Okay. No, we cannot go below silicon atom. Well, that's what happened in deep submicron sub. Because of the density of silicon atoms, the electrons were not able to pass through the silicon atoms. Hmm. Thank you, everyone. Thank you for your nice and kind words. I look forward for many questions. You can reach out to me on my email, or through the Yuvraj sir, you can also reach out to me. Thank you, Yuvraj sir and Neeta ma'am, for giving me this opportunity to be a part of this FDP and allowing me to network with all the faculties across the country. And I'm ready to share my efforts with all of you. Thank you so much.
Thank you, sir, for your
Yeah.
wonderful session. Uh, is there any question? Otherwise, we have to move to the vote of thanks. Any questions from audience?
You can unmute if you want. Otherwise, like many questions he answered.
Okay.
The session was really
I have just unmuted all the participants. So if you have any questions, you can unmute and have a discussion.
I think dinner time do not allow us to ask questions. Then ठीक है,
yeah.
ठीक है, it's okay.
Okay, so
If you have doubts, please write an email to me or Yuvraj sir. He will compile all the list of questions. I will answer them in a neat and nice format.
Okay.
right.
Now I invite Dr. Doshi ma'am to express the vote of thanks. Over to you, ma'am.
Yeah, sure. So with the punchline, knowing happens in classroom, but learning comes in labs. It was really a wonderful session in which this was the first of its kind session in which directly with the hands-on you prove the things, because really the learning happened that time. Many of the concepts, even like back when we were saying that now what next, you have told so many things, what next, so for the new generations to work and proceed with the same zest which they had. So I cannot say bye bye now, but we have to rejoin here again. But thanks a lot, Vinay, back again with so much zest which you gave. So it was really a great pleasure to sincerely thank our esteemed
You're
speaker
most welcome. Thank you so
for an
much.
inspiring and enriching session on CMOS. Like after so many years, I'm back into this world, but it was wonderful. The depth of the knowledge coupled with real world insights. I made some of my students also join, sharing them
Good.
the
Yeah, good,
YouTube
good.
link. So you made the complex concepts both clear and engaging. So the passion with which you shared your expertise truly resonated with all the participants. Like they were UG students, PG students, PhD students, and faculty as well. So we are really grateful for the time, effort. Like I see in the vacation also, you're so dedicated, like you
Yeah.
invested in making this
Lot of
session
missed
so
calls
impactful.
there.
So, on behalf of everyone present here, we
Mm.
extend our heartfelt thanks and we look forward to learning from you again and again and again.
Yes,
So,
ma'am.
once
Certainly
again,
looking
on
forward.
behalf of SVPM and all, I thank you. And really, let's see how we can engage together back again.
Yes, ma'am. Looking forward, and all the best to you all for have a good learning again ahead. There are a
So
lot of great
nice.
people I see down the line in the workshop. You have done an amazing job in
So many days, like, yeah,
collecting
yeah,
all these dignitaries. Natu sir is next. I think he's a pioneer in this world. So have a good
sure,
learning with
sure.
him. Okay, ma'am.
Yes.
Good night,
Okay,
everyone. Thank you
bye.
so
Good
much.
night.
Okay,
Thank you,
bye.
Bye.
sir. Good day.
Thank you.
Thank you.
Bye.
Bye.
Uh, a request to all the participants, fill the feedback form because your attendance will be automatically marked. So you have no escape. If you want your attendance to be there, you have to fill. And I hope maximum of the participants have filled the feedback form.
Ma'am, per day only one attendance sheet or session wise it is there, ma'am?
Pardon?
There is a separate feedback attendance sheet that is session wise. Okay.
Yeah,
Okay,
each
but
session will have its own feedback link.
this session will not get, no?
This session?
I had just
The
pasted
second
the.
session. Only first session I have you forwarded to me, forwarded to us.
No. Both the links are forwarded. Okay.
Okay, sir, shall we check?
Just check one more time, or otherwise I will.
On our participant WhatsApp group, so we can also share the feedback link of both the sessions.
Okay, okay, sir. Okay, ma'am.
Parkai sir, can we do this?
Yeah, yes, ma'am. For first day we will do. Later on we will put in chat box only.
Yeah, yeah. But
Okay.
then from second session, like from the next day, day two, let's be very like sincere. Ki the same sessions will have the link in which you have to fill. Okay. Thank you all the participants for being there. See you tomorrow again.
Yes.
Good
So
night, everyone.
thank you everyone. Okay.
Okay, ma'am. Bye, ma'am. Good night, ma'am.